The universe doesn't just get bigger, it breaks our idea of what big even means, until distance becomes almost meaningless. Zoom out past Earth, past the Sun, past the Milky Way, and the map of reality starts rewriting itself. So where does bigger finally stop? At the edge of space, inside a black hole, or in structures so vast they shouldn't even exist? Tonight, scale stops being a number and becomes a force that reshapes what you think is real. In the deep dark, largest is never just bigger, it's a different kind of boundary. We live inside a universe that hides its true dimensions behind definitions, where an edge can be practical, statistical, or absolute. Our first measurements begin close to home, where the sky's blue is physics and space starts as a negotiated line. The Kármán boundary is not a wall in the air, it's a choice about flight, orbit, and what counts as leaving. From there, distance stops feeling like geography and becomes a language, spoken in light years and parsecs. Even the meter, fixed to light itself, becomes a reminder that scale is built from time. But the farther we look, the more size turns slippery, because objects fade at their outskirts. A galaxy can be measured by its starlight, by its half-light radius, or by the dark halo that refuses to shine. In that darkness, the Milky Way is no longer a simple disk of stars, but a gravitational territory with uncertain borders. The largest galaxies tempt us with record claims, then dissolve into intra-cluster light, where one system blends into another. Clusters change the stakes, because they are not just collections, they are weights in the fabric of space. Their true mass is tallied by motions, X-rays, lensing arcs, and the CMB's faint distortions, each method revealing a different face of the same giant. And then the map becomes something stranger, where object becomes pattern, and boundaries become conventions. Superclusters are drawn by flows and thresholds, by basins of attraction and the web's filaments, not by a clean gravitational edge. At the farthest reaches, the evidence thins, and the universe tests our discipline as much as our imagination. Quasars and gamma-ray bursts become signposts, and the walls they seem to trace demand careful statistics, because a discovery can be real, or it can be the shadow of a method. Just when scale feels almost too vast to hold in mind, the story pivots to a different enormity, an event horizon. A black hole's size is not measured by what it contains, but by what it forbids, where outward paths vanish and geometry becomes destiny. And beyond every catalogue and contour lies the ultimate limit we can speak about with evidence. The observable universe has a horizon set by light and time, expanded by cosmic history into distances that sound impossible, yet remain precisely defined. Across this journey, we will keep returning to one question. When we say the largest, what exactly are we measuring? Diameter, mass, influence, brightness, or the reach of causality? Each answer points to a different universe. This film is an expedition in perspective, built from the tools that make scale legible and the uncertainties that keep it mysterious. Because the cosmos does not merely offer bigger things, it offers bigger contexts, and with them, larger questions. So we begin where every definition begins, with a boundary you can almost touch. Then we follow the measurements outward until the last horizon comes into view. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From Earth's first edge to galaxies, clusters, and the cosmic web, we'll test every definition of largest against what the data can truly support. Then we'll turn inward to black holes, and outward again to the horizon that frames everything we can ever see. We start where big still feels human. A horizon line, a ceiling of blue, a sky that looks like a dome because our eyes and air agree to make it seem that way. Even here, the illusion has physics behind it. Rayleigh scattering favours blue wavelengths, and the atmosphere turns sunlight into a soft, curved-looking canopy. When the sun drops low, the path through air lengthens, and the same scattering warms the light into golds and reds. The question sounds simple at first. How big are the largest objects in the universe? The answer is never just a number, because size depends on what we mean by object. In everyday life, an object has edges you can touch, and a location you can point to. In cosmology, edges can be fuzzy, and locations can be defined by coordinates that stretch with space itself. Begin on the ground, where distance is walked and measured in meters. Scale feels intuitive because it matches our bodies, our cities, and the limits of breath. A meter is a human compromise, but it is also a scientific one. Today it's tied to the speed of light, not a metal bar in a vault. Even our smallest rulers already hint at a universe where measurement is ultimately anchored to light. Then rise into the lower atmosphere, where air still carries sound and weather still matters. The planet's curve is present, but it hides inside familiar geometry. From an airplane window, the curvature is subtle, almost deniable, because your brain is trained to treat the world as flat. Yet the shadow of Earth on a high cloud deck and the way the horizon drops as you climb quietly reveal the sphere. At roughly 10 to 15 kilometers, the stratosphere begins and the rules start to thin out. The sky darkens, the air pressure drops, and the idea of up becomes less personal. The stratosphere is layered and stable, warmed from above by ozone absorbing ultraviolet light. That chemistry matters, because it shapes the boundary between a breathable world and a vacuum that does not care about lungs. Keep climbing, because the first edge in this story is not cosmic. It is a boundary we chose to name, to organize flight, law, and engineering. In the early space age, engineers needed a practical answer to a practical problem. At what altitude do aircraft stop behaving like aircraft? The boundary was never meant to be poetic, yet it became a symbol. Around 100 kilometers above sea level sits the Kármán line, often called the edge of space. It is a useful threshold, not a wall, and nature does not mark it. The idea is attributed to Theodor von Kármán, who noted that as air thins, a wing must move faster to generate the same lift. Eventually, the required speed approaches orbital velocity, and flying becomes falling around Earth. Above it, a vehicle can orbit because speed matters more than lift. Below it, air can still hold you up if you move fast enough. Yet even this is a simplification, because the upper atmosphere does not end abruptly. Satellites in low Earth orbit still feel drag, and their orbits decay unless they are boosted. That ambiguity is the first lesson about bigness. Many edges are definitions, and many definitions are tools, not truths. A definition can still be powerful. Once you draw a line, you can build regulations, design vehicles, and compare missions. But the universe rarely draws such lines for us, and it often punishes us for pretending it does. From here, Earth is already a sphere with a measurable radius, about 6,371 kilometers from center to surface, which is large until you compare it. That number is an average, because Earth is slightly squashed by rotation, bulging at the equator and flattening at the poles. Even our homeworld reminds us that radius can be a model, not a perfect fact. Seen from space, the planet's scale becomes emotional as well as numerical. Thin cloud bands swirl like brushstrokes, and the atmosphere is a fragile haze. The blue edge is not decoration. It is the thickness of the air that keeps oceans liquid. The Moon sits about 384,400 kilometers away on average, close enough to feel like a companion. Yet that gap is already a warning that kilometers will not scale well. The Moon's orbit is elliptical, so the distance changes, and the Moon's apparent size subtly breathes across the month. Ancient skywatchers noticed that rhythm long before they could name the geometry behind it. If we keep counting in kilometers, the numbers become long before the universe becomes large. So astronomy changes units, not to impress, but to stay sane. This is not a retreat into abstraction. It is an admission that the mind handles ratios better than strings of digits, especially when the digits stop fitting into everyday experience. The first step outward is the astronomical unit, the average Earth to Sun distance. 1 AU is about 150 million kilometers, a bridge between human and planetary scales. Historically, pinning down the AU was a triumph of careful geometry, using transits of Venus and the slow accumulation of better observations. Once the AU was known, the solar system snapped into a single, consistent scale. In AUs, the inner solar system becomes readable. Mercury is fractions of an AU away, Jupiter is about 5, and Neptune is about 30. Those numbers also carry a visual rhythm. Tight, fast orbits near the Sun, then widening gaps as you move outward. The spacing hints at how the protoplanetary disk cooled and thinned, leaving different materials to condense at different distances. Even then, the solar system's true reach is not just the planets. The Sun's gravity and its distant debris extend far beyond Neptune, into regions we infer more than see. Beyond the Kuiper belt lies a realm of long-period comets, where objects may take thousands of years to return. The Oort cloud, if it exists as theorized, would be a vast, dim reservoir, more a statistical shell than a photographed place. But the documentary's question is not about our comfort. It is about the largest things that exist and whether thing is the right word. To approach that, we need a unit built from light itself. Light years measure distance, not time, even though the name tempts confusion. A light year is a distance that only makes sense once you accept that light has a finite speed. That fact, measured and refined over centuries, turned the cosmos from an instant panorama into a landscape with delays. 1 light year is how far light travels in a year, about 9.46 trillion kilometers. It is a ruler made from the universe's speed limit. The nearest stars are a few light years away, which means their light began traveling before today's news. Distance immediately becomes a kind of delay. Even the sun is seen 8 minutes in the past, a small reminder that now is local. When we look at a star 4 light years away, we are watching a message launched before many of today's children were born. That delay is not an inconvenience. It is a feature that turns telescopes into time machines, because looking farther means looking earlier. A star seen at 100 light years is seen as it was 100 years ago. A galaxy seen at 1 billion light years is a snapshot from deep prehistory. And because stars evolve and galaxies collide, the past can look genuinely different from the present. The farther we look, the more we see galaxies that are smaller, messier, and more actively forming stars. So size and time start to merge in practice, even if the units stay separate. The biggest structures we will meet are also the oldest images we can access. Astronomers also use parsecs, because geometry and parallax make them convenient. 1 parsec is about 3.26 light years, tied to how angles map to distance. Parallax is the tiny shift of a nearby star against distant background stars as Earth moves around the Sun. It is simple in principle, triangulation with a 1 AU baseline, yet it demands exquisite precision, which modern space missions finally provide. Parsecs scale smoothly into kiloparsecs for galaxies and megaparsecs for the cosmic web. A megaparsec is 1 million parsecs, about 3.26 million light years. These units are not decoration. They are the language that lets us compare a planet, a galaxy, and a filament without drowning in zeros. Now we clarify a second confusion that will haunt every largest object claim. Size is not distance, and apparent size is not physical size. A nearby small object can look larger than a distant giant. A galaxy can fill a telescope image while being smaller than another that appears as a faint smudge. Apparent size depends on distance and on how light spreads, and it can be distorted by lenses of gravity. The universe does not present itself with labels. Gravitational lensing can stretch a galaxy into an arc, or multiply it into several images, because mass bends space-time and redirects light. In those moments, the cosmos becomes its own optical instrument, beautiful and potentially misleading. So when we say something is the biggest, we must specify the metric. Diameter, mass, volume, luminosity, and extent can point to different champions. A diffuse cloud can be enormous in diameter but modest in mass, while a compact object can pack more mass into a smaller region. Even within galaxies, the visible disk and the dark matter halo can imply very different sizes, depending on what you count. Even the word object needs care. A planet is an object. A galaxy is an object. A filament of galaxies may be a pattern that only looks like one. This is where the calm ascent turns into a deeper problem. The larger structures challenge our categories, and they test how structure forms at all. Cosmology begins with a principle that sounds like humility. On the larger scales, the universe is homogeneous and isotropic, meaning it looks roughly the same everywhere. This idea, sometimes called the cosmological principle, is not a claim that everything is uniform. It is a claim about averages, about what remains after you zoom out far enough that local lumps stop dominating the view. That does not mean it is smooth up close. It means that when you average over large enough volumes, the clumps and voids should balance out. Yet surveys reveal a cosmic web of clusters, filaments, and walls. The question becomes how large those patterns can get before the averages win. When we map millions of galaxies, we see strands and knots like a 3-dimensional lacework, with vast voids between. The patterns look almost biological, which raises an uncomfortable question. Are we seeing true structure, or our own hunger for shapes? To ask that honestly, we must define what we can observe. The universe may be infinite, but our view is bounded by light speed and cosmic time. The age of the universe is about 13.8 billion years, measured through expansion, background radiation, and element abundances. That age sets a horizon for information. The cosmic microwave background, a faint glow in every direction, is a key part of that measurement. It is the cooled remnant of an early hot plasma, released when the universe became transparent and photons could finally travel freely. If light has only had 13.8 billion years to travel, you might expect the observable radius to be 13.8 billion light-years. Expansion makes the real number larger. Space itself has stretched while light was in transit. Distant regions were closer when the light left, and they are farther now. Because of that stretching, the radius of the observable universe is about 46.5 billion light-years. The diameter is about 93 billion light-years. This is not because anything broke the light speed limit. It is because the metric that defines distance has changed during the journey. In other words, galaxies are not racing through space faster than light in the usual sense. The space between us can expand, and that expansion can outpace light without violating relativity's local speed limit. So the observable universe is not the whole universe. It is the part whose light has had time to reach us since the beginning of the hot, dense era. Beyond that horizon may be more galaxies, more structures, and more repetitions of the same patterns. Or the rules may shift in ways we cannot test. This boundary is another edge, but unlike the Kármán line, it is not a convention. It is a physical limit on what can be known by observation. Even within the observable region, distance is not a single concept. There is light travel distance, co-moving distance, and the distance implied by redshift. Redshift measures how much the universe expanded while light travelled. It is a proxy for distance and for look-back time, but the mapping depends on cosmology. A spectrum is a barcode of physics. Dark absorption lines mark specific elements, and their shift reveals motion and expansion. When those lines slide toward red, they carry a numerical story about how the scale of the universe changed during the light's journey. So when we call a structure billions of light-years across, we must ask which distance definition is being used. Otherwise, the number can mislead. This is why the documentary begins with measurement. Before we chase the biggest objects, we must agree on rulers, clocks, and what counts as a boundary. Now return to the feeling of ascent, because perception is part of the story. The sky looks like a surface until you leave the air that scatters sunlight. Above the stratosphere, the blue fades into deep indigo, then into a black that feels less like night and more like absence. Stars appear without twinkling, because the atmosphere is no longer there to shake their light. The edge of space teaches that our senses are tuned to local conditions. The edge of the observable universe teaches that our instruments are tuned to cosmic history. Between those edges, bigness becomes a relationship. It is the relationship between an object and the light it emits, between a distance and the time it implies. It is also the relationship between a structure and the theory that predicts it. If a wall of galaxies seems too large, the tension may be in our definitions. Some largest objects will be single-bound systems like giant galaxies or clusters held by gravity. Others will be extended alignments that are not bound as one unit. A cluster can be an object in a strict sense because its gravity ties it together over time. A supercluster may be a region, not a single coherent body. The distinction matters because gravity competes with cosmic expansion, and only some structures are truly bound against the universe's long-term stretching. When we label something a single entity, we're also making a claim about its future. Filaments and walls can be real over densities, yet they may not be stable objects with clear edges. Their boundaries depend on thresholds we choose in data. A map is never neutral. Choose a density cutoff, and a filament appears continuous. Choose another, and it fragments into separate clumps. The largest structures can therefore be partly physical and partly a consequence of how we draw contours. So the central question sharpens. How big can the largest objects and structures truly become? And what do their sizes reveal about the universe's rules? The answer will involve physics, but also statistics. It will involve how matter collapses, how dark matter scaffolds galaxies, and how expansion competes with gravity. Dark matter, invisible to telescopes, dominates the mass budget and shapes the gravitational wells where gas can cool and form stars. Without that hidden scaffolding, the web-like pattern of galaxies would be difficult to explain in the time available. It will also involve humility about what we can claim. The farther we look, the more we rely on faint light, incomplete surveys, and models that translate redshift into maps. Even our best surveys have selection effects. Bright galaxies are easier to count than dim ones, and dust can hide entire populations. When we chase largest, we must ask what we might be missing in the shadows. Still, the maps are real achievements. They show that the universe is not a random spray of galaxies. It has texture, and that texture has a scale. When you watch a three-dimensional visualization rotate, you can see voids like dark cavities and filaments like glowing threads. The view is both scientific and unsettling, because it suggests that emptiness is as much a feature as matter. In this chapter, we have moved from a human edge to a cosmic horizon. We have replaced kilometers with AUs, light years and parsecs, because the story demands it. We have added time to distance because the universe does not let us separate them cleanly. The biggest things we will meet are seen through the lens of evolution. We have also set the tension that will carry the series. The largest objects may be objects, or they may be patterns that only become visible in aggregate, and that raises a quiet, lingering question. When does a pattern become a thing? If the universe is statistically uniform at the larger scales, then every claim of an enormous structure is also a test of that promise. Now we take the next step outward, from near-Earth space into our local neighbourhood of stars. We move from edges and units to the first structures we can truly map. From the Sun's domain, we will enter the Milky Way's disk and halo, where size becomes measured in kiloparsecs, and the word galaxy becomes our next baseline. And once we know the Milky Way's scale, we can begin the real climb. Clusters, superclusters, and the cosmic web will test whether bigger ever runs out. The ascent continues, and the meaning of big will keep shifting under our feet, even when there is no ground left to stand on. Now we take the next step outward, from near-Earth space into our local neighbourhood of stars. We leave the comfort of single suns and enter systems whose edges depend on definitions and on how patiently we observe. The camera pulls back until our solar system becomes a speck, and then even the nearest stars start to look like grains. Distances stop feeling like travel and start feeling like geometry, measured in light years and in the time it takes photons to cross a void. A galaxy feels like a natural endpoint for big, because it is a city of light, packed with billions of suns. It is also a gravitational machine, built from stars, gas, dust, and invisible mass that dominates. That invisible component is not a poetic flourish. It is a measurable influence, written into motions that visible matter cannot explain. When we watch stars orbit, we are watching gravity do accounting, and the numbers do not add up without something unseen. Start with a baseline that is close enough to anchor intuition, and familiar enough to feel like home. The Milky Way's stellar disk spans roughly 100,000 to 120,000 light-years across, depending on how the edge is traced. In wide-field visualizations, it appears as a thin, luminous pancake with spiral structure etched into starlight and dust. From above, the arms would look like pale brushstrokes, with darker lanes where cold dust hides newborn stars. That number is already slippery because the disk fades gradually, rather than ending abruptly. Star counts, gas maps, and surface brightness each draw a different boundary in the same sky. A disk does not stop like a shoreline. It thins into darkness, and our instruments decide where enough becomes none. Even the sun's location inside the disk biases our view, because we are looking through a crowded plane and trying to infer the shape from within. The Milky Way also has a central bulge and a thin and thick disk, each with its own dynamics. Those components overlap in space, and they overlap in the story of how galaxies assemble. The thick disk, for example, holds older stars on puffier orbits, clues that the early Milky Way was more turbulent than it looks today. Their chemistry also tells a story, because heavy elements act like timestamps, marking how quickly earlier generations of stars lived and died. When we picture the galaxy, we often imagine the bright band across Earth's night sky, arcing from horizon to horizon. That band is only the most obvious layer, seen from inside the disk and partially veiled by dust. In infrared views, the dust becomes more transparent, and the galaxy structure appears smoother and more continuous. The bulge brightens, the hidden bar becomes clearer, and the Milky Way looks less like a myth and more like a mapped place. But the disk is not the whole galaxy, and it is not most of the mass we live inside. The Milky Way sits inside a dark matter halo that extends several 100,000 light-years or more. In simulations, that halo is not a neat sphere. It is lumpy, stretched by tides, and threaded with substructure. It resembles a dim, invisible weather system, full of eddies and clumps that never shine. Halo size is inferred from gravity, not from direct light, and that changes how we talk about seeing. We use satellite galaxy motions, stellar streams, and the speeds of halo stars to map the unseen. We also use the way the Milky Way bends the paths of objects, an accounting of acceleration that reveals mass even when it emits no photons. Each tracer is imperfect, yet together they form a consistent picture. The halo is vast, and it sets the long-term boundaries of what remains ours. So the first lesson of this chapter echoes the first edge from chapter 1. Size depends on what you count, and the universe rarely provides a hard line. The more carefully we look, the more boundaries feel like gradients rather than borders. It is a recurring theme in astronomy, because nature does not label its structures for our convenience. If we define size by where most stars live, the Milky Way is a disk with a bright central bulge. If we define size by where gravity still binds matter, the Milky Way is a much larger halo. That halo is the true long-term container, and the disk is a bright, thin ornament inside it. The disk is where the light is concentrated, but the halo is where the gravitational influence quietly dominates. Even bound is conditional because galaxies live in a changing environment, not an isolated laboratory. Tides from neighbours and the pull of the local group reshape the outer halo over time. The outermost orbits are the first to be disturbed and the last to settle into anything like permanence. What is bound today can be loosened tomorrow, especially at the faint edges where gravity is weakest. The local group is small compared to a cluster, but it is not empty, and it is not static. The Milky Way and Andromeda dominate, while dozens of dwarf galaxies trace the shared gravitational landscape. Their paths are like test particles, sketching the contours of an invisible potential. Some dwarfs arrive on plunging orbits, some linger on wide loops, and some are already being torn into streams that wrap around us like faint ribbons. This is where terminology matters, because galaxy types encode different histories, not just different appearances. Spirals like the Milky Way keep rotating disks, while ellipticals are more pressure-supported and merger-built. In a spiral, ordered rotation is the main support against gravity, and that order is fragile. A disk is a kind of memory preserving the direction of angular momentum across billions of years. Spiral galaxies tend to have ongoing star formation in their disks, fed by cold gas and organized by spiral density waves. Ellipticals tend to have older stellar populations and less cold gas, especially in dense environments. In images, spirals look blue and structured, while ellipticals look redder and smoother, like embers after a fire. The colors are not cosmetic, they reflect stellar lifetimes, because massive blue stars burn fast and vanish quickly. The difference is not just appearance, and it is not just age, although both matter. It is a record of how a galaxy gained its mass, and how violently it was disturbed. The shapes of stellar orbits, circular, elongated, random, are fossils of past gravitational shocks. When a galaxy's stars move like a rotating crowd, it suggests long, calm periods, while a swarm of random motions hints at repeated upheaval. In the early universe, small galaxies formed first inside dark matter halos, when the cosmos was denser and mergers were common. Over billions of years, gravity pulled them together into larger systems through mergers and accretion. This bottom-up growth is a central expectation of modern cosmology, and it makes the sky a ledger of collisions. The oldest galaxies we see are not necessarily the largest because size often comes later, assembled piece by piece. Historically, the idea that galaxies evolved through interaction was not always obvious. Early astronomers debated whether spiral nebulae were inside the Milky Way or far beyond it. When that distance scale finally snapped into place, galaxies became separate islands, and then the islands began to show scars. Tidal tails, warped disks, and distorted companions turned speculation into evidence, and the universe started to look like a place where gravity never stops negotiating. Some mergers are gentle and preserve a disk, especially when the intruder is small or the encounter is well aligned. Others are major collisions that scramble orbits, heat the stars and build a rounder, thicker remnant. A disk can survive if the encounter is minor or well aligned, but repeated impacts slowly erase rotation's clean signature. The thick disk of the Milky Way may be one such record, a lingering imprint of early disturbances. When two large galaxies collide, the stars mostly pass by each other without direct impact, because the distances between stars are enormous. The drama comes from gravity, which reshapes trajectories, and from gas, which does collide and shock. Gas clouds compress, cool, and sometimes ignite bursts of star formation. Brief, bright episodes that fade quickly. In visual terms, the collision can light up the overlap region with clusters of hot, young stars like sparks thrown off by a grinding wheel. This is the engine behind the largest galaxies we know, because the bigger systems tend to grow where encounters are frequent. The bigger systems are often found where the traffic is heaviest, in the cores of galaxy clusters. The cluster core is not merely crowded, it is a deep well where orbital energy is constantly being redistributed. In that well, the difference between passing by and being captured can come down to a small loss of energy over many orbits. Clusters are crowded, and their centers are deep gravitational wells that trap both galaxies and hot gas. In those wells, galaxies collide, merge, and sometimes get stripped down to their cores. Some victims lose their outer stars first, leaving compact remnants that orbit like survivors of a long siege. The stripped material does not vanish. It spreads into the cluster, adding to the faint glow that surrounds the central regions. The central giants and clusters have a special name because their role is special. Brightest cluster galaxies, or BCGs, are the products of repeated mergers and cannibalism. They often sit near the cluster's gravitational center, where new arrivals are most likely to be captured. In images, they can look deceptively simple, like smooth ellipses, even though their outskirts may contain the layered debris of many swallowed neighbors. Cannibalism is not metaphorical in the dynamics. It is a predictable consequence of gravity in a dense environment. A massive galaxy can capture smaller ones, and dynamical friction drains orbital energy until the satellite is absorbed. The process is slow but relentless. Each orbit through the halo creates a gravitational wake that acts like a brake. Over time, the satellite spirals inward, and its stars are redistributed into the growing envelope. Over time, the BCG grows a huge stellar envelope, and that envelope can extend far beyond the bright core. It also grows a larger dark matter halo, nested within the cluster's even larger halo. In deep images, the envelope can look like mist around a bright center, fading so gently that the eye cannot find a clean edge. The transition from galaxy to environment becomes less like a line and more like a gradient of ownership. Here, the central question sharpens into a practical problem, because our language wants a single number. When we call a galaxy largest, do we mean its bright core, its faint outskirts, or its total gravitational reach? Each choice is defensible, and each choice tells a different story about what a galaxy really is. The same object can be a champion by one metric and ordinary by another, depending on what we decide to count. Astronomers measure galaxy size in several ways, and each method answers a different question about structure. One can quote a half-light radius, an isophytal diameter, or a model-dependent outer extent. These are not competing truths. They are tools, each tuned to a different part of the light. The choice is often driven by data quality, because the outermost light is where measurements become most fragile. Half-light radius is robust, but it ignores the faintest outskirts, which can hold a surprising fraction of the story. Isophytal diameters depend on a surface brightness threshold, which depends on exposure depth and background subtraction. If you go deeper, the same galaxy grows, not because it changed, but because you finally saw what was always there. That is one of the strangest lessons of deep imaging. The universe can appear to expand as our sensitivity improves. Model-dependent extents can reach farther, but they rely on assumptions about how light falls off with radius. In the outer halo, the signal is weak and the system is easily overfit. A small error in the background can masquerade as a vast halo, or erase a real one into nothing. This is why observers treat the sky background like a measurement in its own right, not a nuisance to be discarded. These are not technical footnotes, because they change the leaderboard and the headlines. The largest galaxies by diameter are often the ones with the faintest, most extended halos. Their most impressive scale lives near the limits of detection, where certainty becomes a careful negotiation. In that regime, the difference between a record holder and a runner-up can be a few photons per pixel, spread across hours of exposure. The history of measuring galaxies is a history of pushing those limits step by step. Early photographic plates revealed bright cores and obvious spirals, but they missed the dim outskirts entirely. Modern CCDs, careful calibration, and long exposures have turned the faint universe into a measurable frontier. Techniques like stacking many images and modelling scattered light have made it possible to see structures that were once invisible, even to large telescopes. One name appears again and again in popular lists, partly because it sits at the intersection of scale and uncertainty. IC 1101 is often cited as among the largest known galaxies by diameter, with estimates reaching roughly 5 to 6 million light-years. In visual terms, that is not a bigger Milky Way, it is a different category of structure. It belongs to the realm of central cluster galaxies, where the environment helps build something that looks almost like a galaxy and a cluster at once. That number is staggering next to the Milky Way's disk, and it forces a recalibration of intuition. It would swallow our galaxy dozens of times over if diameter alone captured the whole meaning of scale. Imagine placing the Milky Way inside it like a coin on a stadium field, and then realizing the field has no fence. The metaphor fails in a useful way, because it highlights that the field is defined by a fading glow rather than a wall. But IC 1101 also illustrates why largest claims are fragile, especially when they depend on the faintest light. Its outer light is extremely faint, and the measured edge depends on where the background is declared to begin. The galaxy's glow competes with the sky's own glow, and the difference can be smaller than the noise. At those levels, the measurement becomes less like drawing a circle, and more like separating two overlapping whispers. At very low surface brightness, the sky itself becomes the enemy, and not just the natural sky. Instrumental scattered light, foreground stars, and imperfect flat fielding can mimic or erase a halo. Even the telescope's optics can spread light from bright sources into a false haze, and that haze can look like a galaxy's outskirts. Astronomers must also contend with faint cirrus in our own Milky Way, dust clouds that reflect starlight and masquerade as extragalactic structure. Observers fight this with careful strategies, dithering, masking, modelling the point spread function, and building accurate sky flats. They also compare independent datasets, because a true halo should persist across instruments and nights. The work is meticulous, and the reward is a map of structure where the eye sees almost nothing. In the final processed images, the galaxy can appear to bloom outward, revealing layers that were always present but never obvious. Even if the halo is real, it may not be purely the galaxy's own, and that is where the definition begins to wobble. In a cluster core, stars can be unbound from any single galaxy and still contribute to the glow. The light we assign to one object may actually belong to the environment, like fog that does not respect property lines. A central galaxy can look larger because it sits inside a shared pool of stars, and the pool does not come with labels. This is the bridge to a concept that blurs the word object, and blurs it for physical reasons. Intracluster light, or ICL, is a diffuse population of stars spread through the cluster potential. It is not a separate galaxy, yet it is not empty space either. It is a shared stellar sea. Those stars still orbit, but they orbit the cluster as a whole, not a single luminous core. ICL forms when galaxies interact and get stripped by tides, especially during close passes near the cluster center. Some stars are pulled into long streams, and over time those streams phase mix into a faint, smooth component. In simulations, you can watch these streams wrap and unravel, until the cluster looks softly illuminated from within. The process is slow, yet it is persistent, and it turns violent events into a quiet, diffuse glow. The cluster becomes a shared stellar environment, and the camera can linger on that ambiguity. The brightest galaxy sits at the center, but its outskirts can blend into the ICL until the boundary becomes an argument. The transition is gradual, and the argument is partly philosophical. Is a star owned by a galaxy, or by the cluster's gravity? When the same star could be counted either way, largest galaxy becomes a question about classification as much as measurement. So the edge of a giant galaxy can be a threshold we choose, set by brightness or by a model fit. It can also be a physical transition from stars bound to one galaxy to stars bound to the cluster. The two ideas do not always coincide, and that mismatch is where the mystery lives. In the deepest images, the outskirts can look like breath on glass, faint and continuous, refusing to resolve into a clean outline. This matters because the documentary's question is not only about numbers, even though numbers anchor the narrative. It is about what those numbers reveal and what they hide about cosmic structure. A single quoted diameter can conceal a complex hierarchy of binding, stripping, and shared gravitational control. The biggest galaxies are often telling us more about their neighbourhoods than about their cores. A galaxy's diameter is one kind of bigness, but mass is another, and the two do not always track cleanly. Two galaxies can have similar sizes in light and very different masses in dark matter. A faint extended halo can add huge diameter with modest additional mass, while a compact system can be massive and dense. The universe is full of structures where the most dramatic visual scale is not the main contributor to gravity. Mass is inferred from gravity, and gravity is what determines long-term fate. From orbital stability to future mergers, rotation curves in spirals and velocity dispersions in ellipticals reveal mass far beyond the visible stars. These measurements are the modern version of weighing the invisible, using motion as the scale. When we plot speed versus radius, we are turning the galaxy into a laboratory, and the stars into test masses. In spirals, stars and gas orbit too fast for the visible matter alone, especially in the outer disk. The flat rotation curve is a signature that the halo dominates at large radii. If only stars and gas mattered, orbital speeds would drop with distance, but instead they stay stubbornly high. That stubbornness is a clue that the mass distribution does not follow the light, and it repeats across countless galaxies. That stubbornness is one of the great observational clues of the 20th century, and it reshaped modern astrophysics. It helped turn dark matter from speculation into necessity, because alternative explanations struggled across many independent galaxies. The pattern repeats so consistently that it feels like a rule, not an exception. The implication is unsettling and elegant at once. Most of what holds galaxies together does not shine. In ellipticals, random stellar motions play the same role, because the stars are not arranged in a cold, rotating disk. The dispersion profile and the behaviour of globular clusters trace the depth and shape of the gravitational well. Planetary nebulae and other traces can extend the measurement farther out, where the starlight itself is too faint. Each tracer is a different kind of probe, like a buoy floating at a different depth in the same gravitational ocean. The largest galaxies are not just large in light, and they are rarely isolated in mass. They tend to sit in the deepest potentials available to galaxies, embedded in cluster-scale dark matter halos. In that setting, galaxy mass and cluster mass are intertwined, and separating them becomes an exercise in definitions. The central galaxy is real, but it is also the brightest knot in a much larger gravitational fabric. This is where black holes enter the chapter, not as a detour, but as a correlation that links small scales to large ones. Supermassive black holes correlate with bulge properties, including mass and velocity dispersion. The link suggests that when a bulge grows, the black hole tends to grow with it, as if both respond to the same supply lines. It is a reminder that growth is not purely additive, because energy feedback can regulate what happens next. The relation is not perfect, but it is persistent across many systems, and that persistence is itself a clue. It suggests co-evolution between a galaxy's central black hole and the growth of its stellar bulge. In plain terms, the smallest region in the galaxy seems to know something about the larger scales of its assembly. How does a region smaller than our solar system end up connected to a structure millions of light years wide? In the biggest ellipticals, the central black holes can be enormous, and their masses can reach billions of suns. In some cases, they push toward tens of billions, making them among the most extreme compact objects known. These are not merely larger versions of the Milky Way's black hole, they are extreme objects that likely grew through both accretion and black hole mergers. When galaxies merge, their central black holes can eventually spiral together, adding another layer to the hierarchy of growth. Those black holes are tiny in physical size compared to the galaxy, and that contrast can be visually striking. Yet they are central to how energy and feedback regulate gas, star formation, and the final appearance of the system. A black hole's influence is not its size, but the energy released as matter falls in and heats the surrounding medium. In the cluster environment, that medium is often a vast atmosphere of hot plasma, ready to radiate and cool unless something keeps it stirred and heated. feedback is part of why giant ellipticals are often red and dead, even when surrounded by gas. Jets and outflows can heat surrounding gas, preventing it from cooling and forming new stars efficiently. In X-ray images, you can sometimes see cavities and bubbles in hot gas, imprints of past outbursts, like scars in a glowing atmosphere. The bubbles rise and expand, and the cluster gas records the event like sediment recording an ancient flood. So the largest galaxies are not just the result of adding more stars, as if growth were a simple pile-up. They are shaped by a balance between infill, mergers, stripping, and the heating of gas in deep potentials. Growth is real, but it is regulated, and the regulator is often the environment itself. The cluster can feed the central galaxy with material, while also preventing that material from forming stars, creating a system that is massive yet quiet. The environment sets the pace, and clusters provide the stage, with timescales measured in billions of years. In a rich cluster core, the relative velocities are high, and interactions are frequent and cumulative. Some encounters are too fast to merge, yet they still leave damage, like repeated close passes that peel away outer layers. The central regions become a kind of gravitational crossroads, where many orbits pass near the same deep center. Some encounters do not merge immediately, but they still strip stars and gas, and they reshape smaller galaxies over time. Harassment and tidal shocking can transform smaller galaxies and feed the diffuse light. A once neat spiral can be distorted into a gas-poor remnant, while its lost stars become part of the cluster's faint glow. The cluster is not only building a central giant, it is also erasing and rewriting the identities of the smaller members. Over time, the central galaxy becomes a record of many histories, layered like geological strata. Its outer halo can contain shells, streams, and gradients that reflect when and how it grew. These patterns are subtle, and they often appear only after aggressive image processing, like fingerprints revealed by dusting powder. When the camera glides across the halo, faint arcs can emerge. Evidence of a smaller galaxy that arrived, was stretched, and then dissolved. Yet even that record is hard to read because the outskirts are faint and easily confused with background. The farther out we go, the more the measurement depends on careful subtraction and deep imaging. A single misestimated background level can tilt the conclusion, turning a modest halo into a mythical one, or vice versa. The uncertainty is not merely statistical, it is observational, rooted in the fact that we are measuring light against light. This is why uncertainty is not a weakness in the story, and not something we should hide from. It is the story, because the universe's largest objects often live where definitions and detection limits collide. When we push to the edge of what we can see, we also push into the edge of what we can agree on. The biggest structures challenge not only our instruments, but our categories, and that challenge is part of their power. We can still compare scales in a disciplined way, and the comparison remains breathtaking even with caveats. The Milky Way's bright disk is about 100,000 light-years across, while the biggest claimed galaxy diameters reach millions. Even allowing for uncertainty, the gap is enormous, and it forces a new intuition about what galaxy-sized can mean. It also reminds us that our home galaxy is not a standard unit, but a single example in a much wider distribution. We can also compare halos, which are often larger than the starlight suggests, and often more physically decisive. A galaxy's halo can extend far beyond its visible edge, and then merge into a larger halo hierarchy. In that hierarchy, the same physics repeats. Gravity gathers, tides strip, and boundaries blur. The deeper we go into the faint outskirts, the more we see that structure is continuous, not neatly partitioned. Hierarchy is the quiet structure underneath the chapter, and it is the architecture that makes largest such a slippery word. Galaxies sit in halos, halos sit in groups, groups sit in clusters, and clusters sit in the cosmic web. The web is not a metaphor, it is the large-scale pattern of matter traced by galaxy surveys and predicted by simulations. In those simulations, filaments feed clusters like rivers, delivering galaxies and gas along preferred directions. At each step, object becomes less obvious, because the boundaries are less about surfaces and more about gravitational influence. The Milky Way is a bound system, but its halo overlaps with Andromeda's in the local group's shared environment. If you could see dark matter directly, the space between the two galaxies would not look empty. It would look connected. The local group would appear as an extended overlapping landscape, with two bright peaks and a broad saddle between them. In a cluster, the overlap becomes unavoidable, and the language of separate islands begins to fail. The BCG and the ICL can be parts of a single extended stellar distribution shaped by the cluster potential. What looks like one galaxy with a huge halo can also be read as a cluster with a bright centre, depending on the question you ask. This dual interpretation is not a trick. It reflects the fact that gravity organises matter across many nested scales. So when we say largest galaxy, we're also asking whether the galaxy is separable from its surroundings in any clean physical sense. The answer depends on the physics we care about and the threshold we choose. Are we tracking starlight, gravitational binding, or the history of assembly written into faint structure? And if our answer changes with the question, what does that say about the way we name things in a continuous universe? This is the narrative tension we need before the next zoom out, because it keeps the mystery alive. Galaxies feel like the natural endpoint of big, until we see they are nodes in something larger. The node can be dazzling, but it is still part of a network that extends far beyond what the eye expects. The camera can show this by letting the bright core shrink, while the faint environment remains, like a stage revealed after the spotlight dims. A node can be luminous and still be a small fraction of the mass, and clusters make that fact unavoidable. In clusters, most baryonic matter is not in stars at all, but in hot intracluster gas. That gas is thin by Earth standards, yet it fills vast volumes, and its total mass can outweigh all the cluster's stars combined. The gas is heated to tens of millions of degrees, and it glows in X-rays because its particles collide and radiate in the deep gravitational well. That gas shines in X-rays, and it traces the cluster's gravitational well with a kind of ghostly precision. It also shows that the cluster is not just a collection of galaxies, but a single massive structure. In X-ray maps, the cluster looks like a glowing atmosphere, and the galaxies are like sparks embedded inside it. The atmosphere can be disturbed by mergers between clusters, leaving shock fronts and ripples that reveal the cluster is still growing. Dark matter dominates even more strongly at the cluster scale, and it provides the main scaffolding. The cluster halo is the true container, and galaxies are embedded substructures moving inside it. Gravitational lensing, subtle distortions of background galaxies, lets us map that dark mass directly as a pattern of curvature in the sky. In lensing reconstructions, the cluster's mass can appear as a smooth mountain range with smaller peaks, and the BCG sits near the highest summit. So the chapter's home scale becomes a stepping stone, not an endpoint, and that shift is deliberate. The Milky Way is our address, but it is not the largest kind of island, and it is not the largest kind of structure. Even our most familiar galaxy is only one luminous knot in a much larger gravitational landscape. The more we zoom out, the more the universe looks less like a collection of objects and more like a connected field, with brightness only marking the densest places. We can summarize the ladder of meanings without losing the mystery, because the ladder is the point. Diameter measures the reach of light, mass measures the reach of gravity, and halos measure the reach of dark matter. Each rung is a different way of answering the same question, and none of them gives a final, clean boundary. The boundaries are chosen, and the choices reveal what we value: light, matter, or influence. Each measure answers a different version of the central question, and the differences are instructive. How big can the largest objects become, and what does that bigness reveal about the rules that built them? And if the rules depend on environment, then perhaps largest is less a trophy and more a clue to where matter flows most efficiently, where gravity is deepest, and where the universe has had the most time to assemble complexity. The rules point toward growth by merging in dense environments, where dynamical friction and repeated interactions do their slow work. The biggest galaxies are often central, often elliptical, and often wrapped in faint light that blends into the cluster. Their scale is not only a product of their own gravity, but of the cluster's ability to deliver material to the center. The central galaxy is, in a sense, the cluster's memory, storing the debris of countless arrivals. The rules also point toward limits that are not absolute walls, and that is part of the unease. The edge of a galaxy is not like the edge of a planet, and the boundary can move with time. As clusters evolve, the balance between galaxy-bound stars and cluster-bound stars can shift, and the definition shifts with it. The largest galaxies may not have a final size, only a current one, measured at a particular epoch with particular instruments. We end where the next chapter begins, with a deliberate shift in perspective and in what we call the main character. A single giant galaxy is impressive, but it is not the dominant structure in its neighbourhood. It is a centrepiece, but the room around it, the cluster, holds most of the mass and most of the story. The camera prepares to widen again, and the central galaxy prepares to lose its monopoly on attention. Now, we zoom out from a single giant galaxy to the cluster that hosts it, where the true giants of matter, gas, and dark matter dominate the scale. The visuals widen until the central galaxy becomes a bright ember in a vast, faintly glowing cloud. Around it, dozens or hundreds of galaxies drift like lanterns in fog, while the real mass remains invisible, inferred from its gravitational pull. The question remains open, and it grows sharper with every step outward, because the universe refuses to give us a final boundary. If galaxies can blur into clusters, then the universe may never offer a final, clean, biggest. Perhaps the real lesson is that scale is relational, defined by context, by physics, and by how deep we dare to look. And as our instruments improve, the edge will keep moving, inviting us to ask again what we mean by an island, and what we mean by home. Now we zoom out from a single giant galaxy to the cluster that hosts it, and the scale shift is immediate. The camera's frame widens until one luminous island becomes a crowded archipelago, and the background fills with faint points that were invisible a moment ago. Clusters are not simply bigger collections of stars because they are the largest structures gravity can hold together for billions of years. In the expanding universe, that phrase, hold together, has a precise meaning, and it is surprisingly hard won. A galaxy cluster is a bound city of galaxies, typically hundreds to thousands of members sharing one gravitational domain. On wide-field images, clusters look like crowded constellations, but their true architecture is three-dimensional and deep. Some members sit in the foreground of the cluster, others far behind, and their apparent proximity can be an illusion of projection. The richest clusters span a few megaparsecs across, measured in the language of large-scale structure rather than everyday distance. 1 megaparsec is about 3.26 million light-years, and the largest clusters occupy several of them. Even that size can be misleading because clusters do not have crisp edges the way galaxies sometimes do. Their density fades gradually into the cosmic web, and their outskirts blur into infalling streams. In deep surveys, you can almost see the transition. Galaxies thin out, then reappear along filaments like beads on dim threads. When we say across, we are already choosing a definition, and that choice will matter later. Mass is where clusters become extreme, because their light is only a hint of their true bulk. The most massive known clusters reach around 10-15 solar masses, 1,000,000 billion suns in one gravitational well. That number is not a trophy label, because it sets the depth of the potential and the temperature the gas can reach. That mass is not packed into a solid object, and it is not even mostly in stars. It is distributed across galaxies, hot plasma, and a dominant invisible halo that outweighs everything we can directly see. This is where the documentary's central question sharpens again, and it becomes almost philosophical. How big can the largest objects become when most of the object does not shine? What does size mean when the main ingredient is dark matter and hot gas? If the brightest parts are only a thin frosting, what are we really measuring when we call something largest? Clusters have ingredients, and the proportions are the first surprise for most viewers. The galaxies are the most visible part, yet they are a minority of the mass by a wide margin. Even the stars inside those galaxies represent only a small fraction of the cluster's total matter budget. Most normal matter is not in stars, and it is not in planets, and it is not in the glowing disks we photograph. It is in the intracluster medium, a thin plasma filling the space between galaxies. Visually, the intracluster medium is almost absent in optical light, so the cluster can look emptier than it truly is. But in X-rays, the scene changes completely. Space between galaxies becomes luminous. The cluster's core often glows like a foggy lantern, with brightness that rises toward the center and fades outward. That glow is not starlight, and it is not dust reflection. It is hot gas radiating because gravity has done work on it. The intracluster medium is heated to tens of millions of degrees by the cluster's gravity, and that heating is not a metaphor. As gas falls into the deepening potential well, it accelerates, collides, and shocks, converting bulk motion into thermal energy. At those temperatures, atoms are stripped into ions and electrons, so the gas becomes a plasma. The plasma emits X-rays through thermal bremsstrahlung, as electrons are deflected by ions and through line emission from heavy elements. Those lines, iron is especially important, carry a record of enrichment by supernovae over cosmic time. That chemical detail matters, because clusters are not pristine. The intracluster medium has been seeded by generations of stellar explosions and galactic winds, and the metals drift outward over billions of years. Some of that material was blown out gently by stellar feedback, and some was torn out violently by ram pressure as galaxies plunged through the hot gas. When we map iron lines in X-ray spectra, we're also mapping the history of star formation and feedback across the cluster's lifetime. Dark matter dominates the mass budget, and it sets the scaffolding for everything else. It does not emit light, and it does not absorb light in any conventional way, yet it shapes orbits and traps gas. In simulations, the cluster is a dark halo first, assembled by the merging of smaller halos in a hierarchical universe. The galaxies and plasma are passengers inside a deeper, wider gravitational structure, and they respond to the same invisible geography. So, big is no longer a simple diameter of starlight, and it is not even a single number. It becomes a combination of mass, extent, and binding, and those are related but not identical. It becomes a question of where gravity still wins against expansion and random motion, and where the cluster's pull becomes only a gentle suggestion. We can measure cluster size in several complementary ways, and each method answers a different version of the same question. We can count galaxies and map their distribution, but that only traces the luminous substructures riding inside the halo. We can measure galaxy velocities, which probe the total mass that keeps the swarm bound. We can also measure the gas, which carries most of the normal matter, and we can measure lensing, which responds to all mass without prejudice. Galaxy velocities are the classical route to cluster mass, and the history goes back more than a century. In the 1930s, Fritz Zwicky measured galaxy motions in the Coma cluster and found they were far too fast to be held by visible matter alone. He coined the term dunkle Materie, dark matter, because something unseen had to supply the missing gravity. At the time, the claim sounded almost reckless, because the missing mass outweighed the visible by an enormous factor. Modern instruments have refined the technique, but the basic logic remains the same. Motion reveals mass, spectra give redshifts, and redshifts give line-of-sight speeds relative to the cluster mean. Each galaxy's absorption lines are shifted by its motion through the cluster's potential, and those shifts can be measured with high precision. With enough member galaxies, the velocity dispersion becomes a thermometer for gravity, because deeper wells produce faster orbital speeds. The virial theorem links that dispersion to the cluster's total mass, translating the chaos of motion into an estimate of the hidden weight. In visual terms, we can imagine a swarm of fireflies in a dark room, and we infer the room's shape by how they bounce. The galaxies are the fireflies, and the room is the gravitational potential, mostly carved by dark matter. The faster the swarm moves, the deeper the invisible room must be. And when the swarm is large enough, the statistics become a kind of clarity. Random orbits average into a measurable signature. The virial approach is powerful, but it assumes the cluster is close to equilibrium, and that assumption is often only approximately true. Real clusters merge, accrete, and slosh, so the mass estimate can be biased if we ignore the messiness of growth. Subclusters can inflate dispersions, and projection can hide structure when unrelated galaxies line up along our sightline. The method works best when combined with other probes, because clusters are not museum pieces, they are construction sites. X-rays provide another route, because hot gas responds to the same potential, yet it carries different information than galaxies do. The gas density profile and temperature profile can be measured across radius, sometimes out to impressive distances with modern observatories. In practice, the analysis depends on how well we can separate faint cluster emission from background noise, especially in the outskirts. If the gas is close to hydrostatic equilibrium, pressure gradients balance gravity, and the equation is straightforward in principle. That balance yields a mass profile, and it also reveals where equilibrium fails, which is often just as interesting. The gas temperature is not a detail, and it is not merely a colour on a false colour map. It is a direct imprint of the depth of the gravitational well, because gravity sets the characteristic speeds of particles in the plasma. Hotter clusters are usually more massive, though mergers can temporarily heat gas beyond its relaxed state. In X-ray images, shocks can appear as sharp brightness edges, while cold fronts show contact boundaries where cooler, denser gas slides through hotter surroundings. Those features are not cosmetic because they are the signatures of assembly. A shock front is a moving boundary where supersonic infill is being thermalized, and a cold front can mark a surviving core from an accreted subcluster. The shapes can look like ripples frozen in place, yet they are the aftermath of collisions on scales larger than galaxies. If we want to understand how clusters grow, we look for these scars, and we read them like tree rings. A third method uses the cosmic microwave background as a backlight, and it is one of the most elegant tricks in observational cosmology. Hot electrons in the intracluster medium scatter CMB photons, shifting their energies through the Sunyaev-Zeldovich effect. The result is a small spectral distortion in the CMB toward the cluster, a decrement at some frequencies and an increment at others. The SZ signal scales with the integrated pressure of the gas, so it is tied to the cluster's thermal energy content. The SZ effect has a key advantage for distant clusters, and it changes what the universe lets us find. Surface brightness dimming with distance does not erase the SZ signature in the same way it erases optical light, because the CMB is behind everything. That is why SZ surveys can find massive clusters far back in time, when the universe was younger and structure was still maturing. The cluster becomes detectable as a subtle shadow in the oldest light we can see, like a fingerprint pressed into the cosmic background. Then there is the most serene and profound clue, because it turns gravity into a map. Gravitational lensing measures mass without asking whether the mass is hot, cold, bright, or dark. A cluster warps space-time, and that curvature redirects the paths of background photons, bending light the way a glass lens bends it, except the lens is made of gravity itself. The effect is predicted by general relativity, yet it becomes tangible when a distant galaxy is stretched into a luminous curve. The visual is almost dreamlike when we see it in deep images. Around the cluster core, faint galaxies behind it are stretched into bright arcs, as if the sky has been smeared by a careful hand. Sometimes the same background galaxy appears multiple times, mirrored and magnified, because the light can take different paths around the gravitational well. The cluster becomes a natural telescope, but also a measurable distortion, and the distortion encodes the mass distribution. Strong lensing appears near the densest cores, where the curvature is steep and the geometry is favourable. Background galaxies stretch into arcs, and sometimes split into multiple images that can be matched by colour and structure. The size of the lensing region reflects the mass concentration and the alignment of distances between observer, lens, and source. In practice, strong lensing lets us pin down the inner mass profile with striking precision, because the arcs are sensitive to the steepness of the potential. Weak lensing works farther out, where distortions are subtle and statistical rather than dramatic. Background galaxies are slightly sheared, their shapes nudged in a coherent pattern that is invisible in any single object. By averaging over many sources, we reconstruct a projected mass map across the cluster's face. That map traces the dark matter halo more directly than any light, because lensing responds to gravity itself. Lensing is quiet, almost gentle in appearance, yet its implication is radical. It shows that most of the cluster's gravity is not where most of the light is, and that mismatch is not a small correction. The mass peaks can align with galaxies, especially in the core, but the smooth component dominates the total. The cluster is a visible city built on an invisible foundation, and lensing lets us sketch the foundation's shape. With these tools, clusters become weighable objects, not just pretty groupings on a star chart. We can estimate total mass, gas fraction, and the distribution of dark matter, and we can do it in multiple independent ways. When the methods agree, we gain confidence that we are measuring the same underlying reality from different angles. We can compare those measurements to simulations of structure formation, where dark matter halos grow through mergers and accretion. We can test whether the universe's growth matches the rules we think it follows, and whether our cosmological model predicts the right number of massive clusters at each epoch. But size still needs an edge, and clusters do not provide a clean one, even when the data are exquisite. The inner region is clearly bound and virialized, where orbits have mixed and the gas is hot and relatively settled. Farther out, matter is still falling in, and the system is still forming, so the physics changes with radius. In the outskirts, the gas can be clumpy, the temperature can drop, and the assumption of equilibrium can fray. The boundary is a process, not a wall, and that makes it both scientifically rich and narratively unsettling. Astronomers often define a virial radius, a practical edge tied to overdensity rather than a visible boundary. Inside it, the mean density is some chosen multiple of the critical density of the universe, which depends on the cosmic expansion rate. Common choices include R200, where the enclosed density is 200 times critical, and related definitions like 500 that focus on denser inner regions. The numbers sound arbitrary, yet they anchor comparisons across instruments, redshifts, and selection methods. It is a convention, but it is a useful one, because it allows clusters to be compared consistently across surveys. Yet simulations suggest a more physical boundary exists in the outskirts, and it is drawn by dynamics rather than bookkeeping. The splashback radius marks where newly infalling matter reaches its first apocenter after passing through the cluster, overshooting the center and slowing at the turnaround point. It is a caustic in phase space, a pile-up where radial orbits slow and reverse, producing a steep drop in density. In a visualization, you can imagine matter streaming inward like traffic, then braking hard at the edge of a roundabout. It is an edge traced by motion, and it reflects how the cluster is growing right now. Splashback is not fixed, because the cluster's growth rate matters, and growth is not steady across cosmic time. Rapidly accreting clusters have smaller splashback radii in scaled units, because the potential is changing while matter falls in. Slowly growing clusters have larger splashback radii, because the potential is more stable, and orbits reach farther before turning. The edge becomes a record of recent assembly, an imprint of the cluster's appetite. It also reminds us that radius is not just geometry, because it encodes time and momentum, so the cluster's outskirts are not empty suburbs, and they are not merely a fading background. They are an active interface where filaments feed the halo, and subclusters arrive with their own gas and galaxies. Gas shocks, galaxies are stripped, and dark matter streams continue inward, sometimes leaving subtle signatures in lensing maps. In optical images, you might see distorted galaxies with truncated gas reservoirs, evidence of ram pressure stripping in action. The cluster is a living structure, still negotiating its boundaries, and its edge is a zone of transformation. This is where the narrative tension deepens, because we are approaching a natural limit. Clusters are the biggest things gravity can truly hold together as single-bound objects, at least in the present-day universe. They are the largest stable cities in an expanding cosmos, and the word stable matters as much as the word large. So what happens when we go larger than gravity can bind? Before we step beyond that limit, we meet a cluster that pushes the internal physics to an extreme, as if it wants to remind us that even the largest bound cities can behave unpredictably. The Phoenix cluster, SPT CLJ2344 42243, is one of the most massive known clusters, and it is among the most luminous in X-rays. It sits at a redshift around 0.6, meaning we see it as it was billions of years ago, when the universe was younger and clusters were still settling into maturity. That look-back time matters, because it places Phoenix in an era when accretion and mergers were more common. In a visualization, Phoenix feels like a bright ember embedded in a darker swarm. The central region shines intensely in X-ray maps, and the optical image shows a dense concentration of galaxies around a dominant central giant. When we overlay the datasets, optical galaxies, X-ray gas and lensing mass, the cluster looks like a layered city plan. The brightest galaxy sits like a civic center, while the hot gas forms a glowing atmosphere around it. Each layer tells a different story, and Phoenix tells them loudly. Phoenix is famous not only for mass, but for its central engine of cooling and star formation, which seems almost too vigorous for a modern cluster. Many clusters have cool cores, where dense central gas radiates X-rays efficiently because emissivity rises with density. In a simple picture, that gas should cool, condense, and form stars at enormous rates, building a blue star-forming central galaxy. Yet most clusters do not show that runaway outcome, and that mismatch became known as the cooling flow problem. The problem is not that cooling is absent, but that it is throttled compared to naive expectations. The reason is feedback, and the main suspect is the central active galactic nucleus, powered by a supermassive black hole. A black hole does not have to shine like a quasar to matter, because mechanical energy can dominate. Jets can inflate bubbles in the hot gas, carving cavities visible in X-ray images as dimples in the glow. Those bubbles rise, stir, and drive weak shocks, distributing energy through the core and offsetting radiative losses. Over time, the bubbles can leave a ghostly pattern, like footprints in a luminous fog. In that regulated picture, the cluster core becomes a thermostat with imperfect wiring. Gas tries to cool, sink, and condense, while the AGN responds by injecting energy that reheats and reorders the plasma. The balance is not static because the AGN can flicker and the gas can respond in cycles. The cooling time can shorten, the black hole can feed, and the jets can reignite. Then the cycle resets. Over time, many clusters appear to hover near a state where cooling is slowed enough to prevent a starburst, yet not stopped entirely. Phoenix challenges that balance by appearing to cool too efficiently, as if the thermostat has failed at the worst moment. Observations indicate an extreme cooling flow and an unusually high star formation rate in the brightest cluster galaxy. The central galaxy is not quiet and red, and it is not merely forming a few stars on the side. It is forming stars at a pace that feels more like the early universe than a mature cluster core. In the core, cold gas and young stars become a bright counterpoint to the surrounding X-ray blaze. That contrast is part of what makes Phoenix so haunting, because it looks like a relic of an earlier cosmic era embedded in a later one. In wide shots, the cluster is an enormous mature structure, yet in the centre the gas behaves as if it has permission to collapse. The core becomes a stage where gravity, radiation and black hole feedback argue in public. We are watching a negotiation between heating and cooling that the cluster may be losing, at least for now. This is not just a curiosity about one object, and it is not merely a record holder. It is a stress test for feedback models across cosmic time, because the same physics is invoked to explain why most cool cores do not catastrophically cool. If AGN heating is universal and effective, why does Phoenix look like it is slipping the leash? If cooling can sometimes outrun heating, what sets the boundary between regulation and runaway? And if the boundary can move, how often does the universe cross it without us noticing? The answer may involve timing, geometry, and how energy couples to the gas, and those details can matter more than raw power. Jets can miss dense clouds, or deposit energy at the wrong radius, heating the outskirts while the center continues to cool. Cooling can become multi-phase, with cold filaments forming inside hot plasma, and those filaments can feed both star formation and the black hole. Magnetic fields and turbulence can influence how heat is transported, even when the overall energy budget seems sufficient. The core becomes a complex ecosystem rather than a single temperature atmosphere, and the word core starts to feel too simple. In images of other cool core clusters, we sometimes see filamentary structures traced by emission lines, draped like luminous threads around the central galaxy. Phoenix evokes that same kind of texture, but amplified, as if the cluster is weaving cold gas out of hot plasma. The filaments can look like river deltas of light, branching and curling around dark lanes of dust. The question becomes not only how much energy is injected, but where it goes and what it does on the way. Phoenix also reminds us that clusters are not static containers, even when their masses are enormous. Their central galaxies are built by mergers, cannibalizing smaller galaxies that spiral inward through dynamical friction. Their gas is shaped by feedback and accretion, and their dark matter halos deepen over time, changing the conditions for cooling. Even at the cluster scale, big is not just size. It is an evolving balance of processes that can tip, recover, and tip again. When we weigh Phoenix, we use the same toolkit, and we rely on the same cross-checks that make cluster science robust. X-ray temperatures indicate a deep potential well, because only a massive halo can heat gas to such extremes. The SZ effect confirms a large integrated pressure, revealing the thermal energy stored in the intracluster medium. Lensing reveals the mass distribution, including the dominant dark matter component, and it does so without caring about the gas's state. Multiple methods converge on the conclusion that Phoenix is truly massive, and that convergence is part of the confidence. Yet the core physics remains the mystery, because mass alone does not predict star formation, and Phoenix proves it. Two clusters can have similar total mass and very different core behavior, ranging from quiescent to wildly active. The difference is in entropy, cooling time, and the history of feedback, which are shaped by mergers and by the black hole's duty cycle. Even subtle differences in how gas is stirred can change whether it condenses into clouds or remains suspended as plasma. The biggest objects still contain local puzzles, nested inside their global scale like riddles inside a map. Clusters also act as laboratories for dark matter itself, and the evidence is written in their collisions. Lensing maps can show offsets between gas and total mass in merging systems, where the components separate. The hot gas feels pressure and shocks, so it can slow down and lag behind in a collision. Dark matter, if it is truly collisionless, passes through with minimal interaction, staying aligned with the galaxies more than with the gas. That separation is not just a dramatic visual, and it is not just a headline. It helps constrain how strongly dark matter can interact with itself, because too much interaction would cause it to behave more like the gas. Even when there is no dramatic merger, lensing shows the smooth dominance of dark matter, and it reveals subhalos associated with member galaxies. Those subhalos are embedded in a larger halo, and they are being stripped and reshaped by tidal forces as they orbit. In a sense, the cluster is a wind tunnel for gravity, testing what matter does when it cannot radiate its energy away. It shows that the cluster is not just a pile of galaxies sitting in empty space. It is a hierarchy of halos inside halos, a nested structure that reflects the way the universe builds complexity. The galaxies are the visible residents, but the city's zoning laws are written by dark matter. And the intracluster medium is the atmosphere, thin, hot and luminous in X-rays, responding to every merger like weather. So the cluster becomes a new kind of largest object in the series, and it forces us to refine what we mean by object. It is not defined by a bright edge, but by a gravitational domain that can be measured in several independent languages. It is measured by motion, by heat, by distortions in background light, and by shadows in the microwave sky. Its true bulk is invisible, yet its influence is unmistakable, and that is why clusters feel both real and uncanny. This returns us to the opening hook, now reframed at a higher rung of scale, where the stakes feel cosmological. If you could zoom out forever, would the universe run out of bigger? Clusters suggest a partial answer because they look like a limit imposed by expansion. They are the largest bound structures, and the word bound matters, because it separates a lasting object from a temporary pattern. In a universe with accelerating expansion, that distinction becomes sharper with time, not softer. But the sky contains structures that look larger than clusters, and that is where definitions become dangerous again. Superclusters, walls and filaments can span tens to hundreds of megaparsecs, and they dominate the maps of large-scale structure. They can look like single objects in surveys, especially when we draw contours and connect over densities into continuous shapes. In visualizations, they resemble luminous rivers and branching deltas, with clusters as bright knots along the flow, yet they are not necessarily single-bound entities, and appearance can be a trap. The difference is not semantic, and it is not merely about how we draw boundaries on a map. It is physical, because cosmic expansion competes with gravity on large scales, and the competition has a measurable outcome. A cluster's interior can decouple from expansion and remain bound, with galaxies orbiting rather than drifting away. A supercluster may be an association still stretching, still flowing, and destined to fragment into separate bound nodes. The future becomes part of the definition, and that is an uncomfortable but honest twist. So we end this chapter with a boundary that is both measurable and mysterious, because it exists in more than one form. The cluster edge can be defined by overdensity, and it can be defined by splashback dynamics, and each definition reveals a different aspect of reality. Both edges are real in their own way, and neither is a hard surface you could fly a ship into. The biggest bound cities have outskirts that are still being built, and their growth is written in shocks, streams and turning points. And beyond them, the next scale waits, tempting us with shapes that may be structures or may be patterns, depending on how gravity and expansion settle the argument. We step beyond clusters to superclusters, vast associations in the cosmic web, where filaments connect nodes like glowing highways. They look like continents, but gravity may not hold them as one, and that uncertainty becomes the next mystery. The next chapter asks what big means when even binding becomes uncertain, and when the universe itself refuses to draw a clean line. We step beyond clusters to a scale where object becomes pattern, and boundaries become arguments. The central question returns with new force, because the map keeps widening and our language starts to strain. How big can the largest structures become, and what does their size truly mean in physics? On screen, the familiar galaxy fields begin to thin into a wider panorama, as if the camera is pulling away from a city into weather systems. Individual galaxies fade into points, then into a grainy mist, until only the densest regions remain obvious. What looked like separate islands at cluster scale starts to resemble weather, fronts, streams, and converging currents across a vast sky. Clusters felt like a natural limit because gravity can bind them for billions of years, even while space expands around them. A rich cluster is a true gravitational system, with galaxies orbiting inside a shared dark matter halo that outweighs the visible stars by far. Hot intracluster gas glows in X-rays, and that glow is a sign of deep potential wells and violent heating. These are structures that have largely decoupled from cosmic expansion, at least within their cores where gravity dominates. That decoupling has a measurable signature because the gas temperature tracks the depth of the gravitational well. In massive clusters, the plasma reaches tens of millions of Kelvin, so hot that atoms are stripped and X-rays pour out. Gravitational lensing adds another line of evidence, bending background light into arcs that trace mass whether it shines or not. Clusters, in other words, are not just collections of galaxies. They are laboratories where dark matter, baryons, and gravity reveal themselves together. Superclusters look larger than that limit, yet they are not simply bigger clusters with a single center. They are regions where many clusters and groups share a broader gravitational landscape, even if they do not share a single bound fate. Their shapes are drawn by filaments, voids, and the long memory of cosmic expansion, which keeps stretching the stage. In many cases, the supercluster is less like a city and more like a watershed, an organizing terrain. This is the cosmic web, the large-scale arrangement of matter across the observable universe. Galaxies trace it because they form where dark matter is densest, and dark matter provides the scaffolding that collapses first. The web has filaments that connect, nodes where filaments intersect, and voids where matter is scarce and flows outward. It is not a metaphor, and it is not a decorative pattern. It is the outcome of gravity, amplifying tiny early differences in density. On screen, the web can be rendered as a translucent lattice, with bright knots and faint strands suspended in blackness. Filaments appear like braided fibers, sometimes splitting and rejoining, while voids open as smooth, dark bubbles between them. The camera drifts along a filament toward a node, and the density rises almost imperceptibly at first. Then the scene thickens. Galaxies crowd together, and the node becomes a gravitational crossroads. In simulations, the web appears as a living network, with thin strands feeding thicker trunks that funnel matter into nodes. Gas flows along those strands, shocks heat it at filament boundaries, and cooling allows it to condense into galaxies and groups. The brightest galaxies often sit at nodes, where multiple filaments meet and merge as a common over cosmic time. Even the directions of galaxy spins can carry faint memory of filamentary accretion, subtle but measurable when surveys become large enough. Those differences were small in the beginning, yet they were not zero, and that fact is the seed of everything we see. In the early universe, density fluctuations were imprinted across space, seeded by quantum variations stretched during inflation into macroscopic ripples. In plain terms, the young cosmos was almost smooth, but not perfectly smooth, and that imperfection mattered. Gravity pulled slightly denser regions into stronger growth, while underdense regions emptied out and became the first voids. The growth is not uniform across scales, and that detail matters when we ask what can become largest. In the radiation-dominated era, pressure and relativistic effects suppressed collapse on small scales, because photons resisted compression and carried energy away. After matter began to dominate, cold dark matter could clump efficiently, because it does not feel radiation pressure and interacts weakly. Baryonic matter followed later, falling into dark matter wells, cooling through atomic processes and lighting them up with stars. The cosmic microwave background carries the earliest clear map of those fluctuations, and it is one of the most precise datasets in science. The CMB is the relic light from when the universe first became transparent, about 380,000 years after the Big Bang. Before that time, photons scattered constantly off electrons in a hot plasma, and the universe was effectively opaque. When electrons combined with protons to form neutral atoms, light finally streamed freely, leaving behind a snapshot. Its temperature variations are tiny, yet they are the blueprint of later structure, encoded in a pattern that can be analysed statistically. The fluctuations are only tens of microkelvin on a 2.7 Kelvin background, a contrast of roughly 1 part in 100,000. Yet those faint mottles encode the statistical seeds of everything that followed, including the preferred scales set by early sound waves. When we compare CMB statistics with galaxy surveys, we see the same story at different times, separated by billions of years. On screen, the CMB's speckled oval map slowly dissolves into a 3-dimensional simulation. Bright and dark patches stretch into filaments, and the filaments thicken into the regions where clusters will later form. A faint grid of co-moving coordinates appears, then fades, reminding us that expansion is part of the geometry. The transition is not literal, but it is conceptually faithful, an early pattern becoming a late-time architecture. The web also expresses the cosmological principle in a subtle way, and that subtlety is where debates begin. On small and intermediate scales, the universe is highly structured and clumpy, with dramatic contrast between nodes and voids. On very large scales, the distribution approaches statistical uniformity, meaning no direction or location is special on average. The tension is not a contradiction, but a question about where large enough begins, and how we decide. That question has a history, and it shaped modern cosmology in the era of expanding redshift surveys. Early galaxy maps hinted at walls and chains, and astronomers debated whether the universe might be fractal at all scales. The discovery of prominent features, like the Great Wall in the late 1980s, sharpened the argument and forced better statistics. As surveys expanded and methods improved, the picture settled toward homogeneity at sufficiently large scales, even though striking structures persist. Still, the boundary between structured and statistically smooth is not a sharp line, and it depends on how we measure. Do we average number counts in spheres, examine correlation functions, or test topology with genus statistics? Each method emphasizes a different aspect of the same distribution, and each has its own sensitivity to bias and sampling. The universe does not hand us a ruler labeled homogeneous beyond here, so we build the ruler ourselves. Superclusters sit in the middle of that tension, occupying scales where the web is unmistakable, yet not necessarily bound. They can span hundreds of millions of light years, and their outlines can look like continents on a map drawn from galaxy density. Yet they often fail the strict definition of a single bound object, because the gravitational pull is spread across long filaments. Expansion competes with gravity, and on these scales the competition can prevent full binding. In an accelerating universe, that competition becomes even more decisive, because the background expansion is not merely coasting. Dark energy drives the expansion to speed up over time, making it harder for widely separated regions to collapse together in the future. A cluster can remain bound because its internal gravity is strong and its crossing time is short. A supercluster, spread thin across filaments and void edges, may never fully assemble into one gravitationally relaxed entity. So we define superclusters carefully because the definition changes the story we tell and the physics we imply. Some are identified by galaxy density, using thresholds that connect nearby overdensities into extended regions that look continuous on a smoothed map. Some are defined by filament connectivity, linking clusters along preferred directions in the cosmic web, like highways between nodes. Some are defined by dynamics, using galaxy motions to trace basins of attraction and the ridges between them. Each definition is useful, and none is final, because each is a lens with its own distortions. Density thresholds depend on survey depth and smoothing scale, because the same field can look continuous or fragmented depending on resolution. Connectivity depends on how we choose to connect filaments in noisy data, where gaps can be real or simply unobserved. Dynamics depends on how well we can measure distances and velocities in the nearby universe, where errors propagate into the flow field. The documentary's hook returns in a new form, and it sounds almost philosophical even though it is rooted in measurement. If you could zoom out forever, would the universe run out of bigger, or would bigger keep reappearing as a new kind of pattern? At the supercluster scale, bigger can mean a larger gravitational basin, or a longer filament, or a wider void. The answer depends on whether we are counting objects or mapping flows, and those are not the same question. To map flows, we need to separate two kinds of motion, which look similar in redshift but mean different things. Galaxies recede from us because space expands, and that recession increases with distance in a nearly linear way nearby. This is the Hubble flow, and it sets the baseline trend of redshift with distance, like a background current. On top of that baseline, gravity adds deviations that carry extra information about mass distribution. In practice, the Hubble flow is a remarkably clean first approximation, which is why it transformed cosmology so quickly. A galaxy twice as far away is, on average, receding about twice as fast, and the scatter around that trend is informative. Yet the universe is not a perfect grid, and galaxies are not just passengers carried outward. They fall toward overdensities, stream along filaments, and drift away from voids, motions that slightly tilt the local expansion map. Those deviations are called peculiar velocities, and they are the key to this chapter because they turn motion into a probe of invisible mass. Peculiar velocity is a galaxy's motion relative to the smooth expansion, measured after subtracting the Hubble trend expected at its distance. It can be toward an overdensity, away from a void, or along a filament where gravity channels motion. It is usually smaller than the Hubble recession at larger distances, yet it is decisive nearby, where structure is strongest. On screen, arrows appear over a three-dimensional galaxy map, each arrow a small correction to the overall outward flow. Most arrows are modest, but they align in coherent regions, like wind vectors over an ocean that reveal pressure systems. Where arrows converge, the map hints at hidden mass, even if the galaxies there are partly obscured. Where arrows diverge, the map reveals the silent influence of emptiness, as voids push matter outward by being underdense. Measuring peculiar velocity is difficult, because it requires independent distances, not just redshift. Redshift alone mixes expansion and local motion into one number, and the two cannot be separated without extra information. We estimate distances using standard candles and scaling relations, then compare expected Hubble recession to observed redshift. The difference becomes a velocity that traces hidden mass, but only after careful calibration and error control. The distance ladder is a toolbox, and each tool has limits that become obvious when precision matters. Cepheid variables provide reliable distances in nearby galaxies because their pulsation periods correlate with luminosity through well-tested physics. Type Ia supernovae extend that reach because their peak brightness is standardized after calibration and light curve corrections. For spiral galaxies, relations like Tully, Fisher link rotation speed to luminosity, offering distances when supernovae are absent and Cepheids are too faint. Every step introduces scatter, and scatter matters when velocities are only a few hundred kilometers per second. A small distance error can masquerade as a large peculiar velocity because the inferred Hubble recession changes with distance. That is why flow maps are built from many galaxies, averaged and smoothed to reduce noise and reveal coherent patterns. The goal is not perfection for one object, but a coherent field across space that can be compared to theory. Peculiar velocities reveal what light alone can miss, because gravity responds to total mass, not just luminous mass. Dark matter dominates the mass budget, and it shapes the gravitational potential across the web, setting the wells and ridges that guide motion. Galaxies respond to that potential whether or not we can see the mass directly in stars or gas. When we map many peculiar velocities, we reconstruct a flow field across the local cosmos, like inferring wind from drifting leaves. A flow field turns the sky into a landscape of basins and ridges, and it changes how we talk about belonging. In this landscape, a basin is a region where flow lines converge toward a common attractor, indicating a shared dynamical tendency. A ridge is a boundary where flows diverge toward different attractors, like a continental divide in geography. These are not drawn by brightness, but by dynamics, by how galaxies actually move through expanding space. This is where Laniakea enters, not as a single object with a crisp edge that you could circle on a photograph. Laniakea is our home supercluster, defined primarily by galaxy flows rather than by a simple density contour, and that choice is the point. Its scale is about 520 million light-years across, roughly 160 megaparsecs, which is vast by any human intuition. The number is enormous, yet the meaning lies in how the boundary is chosen and what that boundary represents. The name itself carries a quiet intention, and it fits the tone of a structure defined by motion. Laniakea comes from Hawaiian, meaning immense heaven, and it signals a shift in perspective from objects to trajectories. We are not naming a fortress of galaxies, but a region of shared motion through a gravitational landscape. The term invites a different question, not what is it made of, but where is it going and with whom? Laniakea was mapped by combining distances and peculiar velocities for thousands of galaxies, most within the nearby cosmic volume. The method builds a three-dimensional velocity field, constrained by observations and smoothed to suppress random errors while preserving coherent flows. From that field, researchers trace streamlines that show where galaxies are moving relative to expansion, like dye injected into a flowing river. The streamlines converge toward a region associated with the Great Attractor, which becomes the basin's dynamical focus. Visually, the streamlines look like luminous threads in a dark volume, and the effect is both elegant and slightly uncanny. They curve gently, then bend more sharply, as if pulled by an unseen hand that grows stronger near the node. Some threads spiral into knots where clusters sit, while others peel away along ridges that mark competing basins. The motion makes the structure feel real, even when density boundaries remain uncertain. Movement becomes the outline. The Great Attractor is not a single monster object, and it is not a simple point that you could mark with a pin. It is a direction and a region where mass concentrations create net pull on surrounding galaxies, producing coherent, peculiar velocities. Some of that mass is obscured by the Milky Way's plane, where dust and stars hide background galaxies and complicate surveys. The attraction is inferred from motion as much as from light, which is exactly why flow mapping matters. That obscured region is sometimes called the zone of avoidance, and it is a reminder of our observational limitations. Even with infrared surveys and radio maps of neutral hydrogen, some structures remain harder to sense as behind the galactic disk, where extinction and confusion rise. Yet gravity does not care about our line of sight, and the universe does not rearrange itself for our convenience. A hidden concentration still tugs, and peculiar velocities still register the pull in the motions of visible galaxies. In the Laniakea picture, the key idea is a watershed boundary, and the metaphor is more than poetic. A watershed is a dividing surface between drainage basins, familiar from geography and river maps, where a drop of rain chooses one valley or another. Here it separates regions whose flow lines converge toward different attractors in the cosmic web. Inside the watershed, galaxies tend to flow toward the same basin. Outside it, the flow turns toward other basins, implying a different long-term dynamical affiliation. This boundary is powerful because it is physical in a dynamical sense, not just a contour drawn on a density plot. It is not simply where galaxy density drops below a threshold, which can be sensitive to sampling and smoothing. It is where the direction of motion changes in the reconstructed field, an actual change in the inferred gravitational landscape. Yet it is also model-dependent, because the field reconstruction depends on data quality, smoothing choices, and assumptions about how velocities relate to mass. That dependence is not a weakness so much as a caution label, and good maps advertise their uncertainties. If the sampling is sparse in one region, the reconstruction may blur a sharp ridge into a gentle slope, shifting the watershed boundary. If distance errors are correlated, a spurious bulk flow can appear, and the basin can seem larger or smaller than it is. The watershed is meaningful, but it is meaningful within the assumptions that build the map. Physics filtered through measurement. Laniakea also reframes our sense of home, because it nests familiar structures inside a much larger dynamical context. The Milky Way is in the local group, a small assembly dominated by the Milky Way and Andromeda, along with dozens of smaller satellites. The local group sits near the Virgo region, associated with the Virgo cluster and its surrounding structures, which influence local motions. That neighbourhood, in turn, sits within this larger flow basin, where many pulls add into one coherent drift. Our galaxy's motion is not random, and it is not only about local neighbours within a few million light-years. It includes a component driven by large-scale structure, accumulated across many pulls and pushes that add like vectors. Nearby masses like Virgo matter, but so do more distant concentrations, because gravity's influence extends far and the net effect can be coherent. The result is a drift through the expanding universe that encodes the mass distribution of our region. The CMB provides an independent anchor for that motion, and it is one of cosmology's cleanest measurements. We see a dipole anisotropy in the CMB caused by our motion relative to the CMB rest frame, which acts like a cosmic standard of rest. One side of the sky looks slightly hotter, the opposite slightly cooler, because of a Doppler shift in the microwave photons. That dipole indicates a speed of about 370 km per second for the solar system barycenter, and it is measured with exquisite precision. Part of that motion reflects pulls from nearby structures and larger basins, and part reflects the local group's motion within its environment. The key point is conceptual. The CMB defines a cosmic rest frame, and we are not at rest in it. Our motion becomes a clue, and superclusters become suspects, but the case is rarely one-to-one. The observed dipole is the sum of many influences, and disentangling them is part of the scientific drama. So Laniakea becomes a bridge between local astronomy and cosmology, tying together different kinds of evidence. It links galaxy surveys, distance ladders, and the CMB into one narrative about motion and mass. It also shows how largest can be defined by motion rather than by light, which is a subtle but profound shift. The structure is not a wall, but a pattern of converging trajectories that makes the local universe feel like a landscape. Yet Laniakea is not the end of the story, even in the nearby universe, because the web is not organized around a single sink. The local web contains other major concentrations that compete for influence, shaping the flow field like neighboring valleys separated by ridge lines. Some lie beyond Laniakea's watershed boundary, drawing flows in different directions and reminding us that boundaries are relational. The web is a network of basins, not a single drain, and the map only makes sense in context. If we could hover far above the local cosmos, the scene would resemble a topographic map made of gravity, with slopes defined by potential rather than altitude. Some regions would slope toward one attractor, others toward another, and the ridges between them would be subtle and sometimes braided. Those ridges are not empty lines, but places where the net pull balances and small uncertainties can flip the inferred direction. In that balance, the definition of belongs to becomes a matter of dynamics, not identity. To scale up, we move toward one of the most massive nearby nodes, the Shapley Supercluster, which looms as a dense knot in redshift space. Shapley is a vast concentration of galaxy clusters and groups, rich enough to stand out even in coarse surveys and early catalogues. It lies roughly 650 million light-years away, in the general direction of the constellation Centaurus, and it occupies a notable volume of the nearby universe. It is often described as one of the most massive structures in our cosmic neighbourhood, and that description has consequences for motion. Historically, Shapley's prominence emerged as redshift surveys improved in the late 20th century, when cluster distances could be measured more systematically. As astronomers built larger catalogues and plotted clusters in 3 dimensions, a remarkable concentration appeared in that part of the sky, too strong to ignore. The name honours Harlow Shapley, whose earlier work mapped the Milky Way's size and the Sun's position within it, shifting humanity's self-image. It is fitting in a way that another map would later bear his name, again pushing our sense of place outward. Shapley matters because mass on that scale can affect large-scale motions, not by rewriting expansion, but by adding a coherent gravitational tug. The local universe shows coherent flows over tens to hundreds of megaparsecs, visible as bulk motions relative to the Hubble expansion. Some of that motion is attributed to overdensities like Shapley, acting as a deep node in the nearby web that can bias velocities. The details remain an active area of measurement and modelling, because multiple structures contribute and the data are never perfectly complete. In the flow picture, Shapley is less a destination than a gravitational landmark, a deep intersection where the web thickens. It is a place where many filaments terminate or pass through, and where cluster densities rise and the potential deepens. The surrounding velocity field can show a subtle tilt toward it, but the signal competes with other attractors and with observational uncertainty. Yet even here, the word supercluster must be handled with care, because richness does not automatically imply a single-bound fate. Shapley is not a single-bound object either, and that is part of the theme that keeps returning at larger scales. It is a region of enhanced density with many rich clusters, each cluster a bound system in its own right with its own hot gas and dark halo. Its gravity deepens the web's node, and filaments feed into it like tributaries into a delta. It acts like a major intersection in the nearby cosmic network, even if the network itself is not a single entity. On screen, the visualization tightens around Shapley's direction, and the map becomes crowded as the density rises. Dots thicken into clumps, then into a knot of clusters, with labels flickering on and off as the camera passes through. Filaments appear as faint bridges, and the voids around them look like dark bays carved out of the distribution. The impression is of a cosmic metropolis, but one built from gravity rather than streets, and assembled over billions of years. Comparing Laniakea and Shapley clarifies what supercluster can mean and why the same word can hide different physics. Laniakea is defined by a flow basin and a watershed boundary, emphasizing coherent motion and dynamical affiliation. Shapley is often emphasized as a massive concentration and a dominant node, emphasizing density and cluster richness within a region. Both are real structures in the web, yet their edges are not equivalent, and the distinction matters when we talk about size. This is the point where the documentary's language must stay careful, because numbers without definitions can mislead. When we say across, we might mean a diameter traced by streamlines in a velocity reconstruction, which depends on smoothing. We might mean a span across connected overdensities in a density map, sensitive to thresholds and survey completeness. We might mean the extent of a filamentary complex in redshift space, where distortions can elongate or compress features. Each choice produces a different number and a different headline, even when the underlying universe is the same. The deeper issue is that superclusters may not be gravitationally bound as wholes, which makes them different from clusters in a physically important way. Parts of them can be bound into clusters and groups, where galaxies orbit and hot gas remains confined in a shared halo. Other parts may be stretching with expansion and will never collapse into one object, even if they look connected today. In an accelerating universe, many large associations are temporary patterns, not future single entities, and that temporariness is part of their mystery. That future matters because binding is a physical criterion, not a naming preference, and it speaks to destiny. A bound structure has a shared fate, orbiting and merging within one potential over cosmic time until it relaxes into equilibrium. An unbound association can disperse, leaving only its densest nodes as separate islands, while filaments thin and drift apart. Superclusters often sit on the dividing line between these outcomes, making them liminal structures, real yet not fully unified. One way to picture that dividing line is to imagine the web as a set of beads on elastic threads, stretched across a slowly expanding frame. The beads, clusters, hold together because their gravity is strong and their internal motions are fast. The threads, filaments, can stretch, thin, and even break in a dynamical sense, as expansion outpaces collapse at their edges. The supercluster is the arrangement of beads and threads, not necessarily a single bead, and that distinction changes what largest means. The cosmic web also includes voids, and voids belong in a chapter about bigness because emptiness can be a sourmus. A void is not merely empty space between interesting things, and it is not truly empty, because it still contains dark matter, gas, and sparse galaxies. It is a region of low density that can span tens to hundreds of megaparsecs, comparable to supercluster scales. Voids shape the geometry of filaments by pushing matter outward and defining where flows diverge, like negative gravity wells. Voids expand faster than the average because they are underdense, so gravity slows them less, and matter evacuates their interiors over time. Matter drains from them towards surrounding filaments and walls, and that drainage is an organized process rather than a random diffusion. It contributes to peculiar velocities, as galaxies near voids can have motions away from the void center, adding a repulsive-looking component that is really just reduced deceleration. In the flow picture, voids are sources of divergence, complementing attractor basins and completing the landscape. Visually, voids are the negative space that makes the web legible, like silence that makes music intelligible. In galaxy maps, they appear as great dark cavities, outlined by arcs of galaxies like shorelines around a sea. In simulations, they are smooth, ballooning regions where filaments form the boundaries and the interior looks almost washed clean. The emptiness is not nothing. It is a dynamical environment with a measurable effect on motions, lensing, and the growth of structure. Voids also complicate our intuition about structure boundaries, because edges can be defined by absence as much as by presence. A filament can look continuous because it wraps around a void, creating a long, curved chain that reads as one feature. A wall can appear because galaxies outline the void's edge, exaggerating the sense of a sheet even when the density is modest. In maps, emptiness can be as coherent as density, and sometimes easier to define because the contrast is sharper. So bigness becomes dual, and that duality is part of the mystery that keeps the chapter alive. We can talk about the biggest concentrations of matter, like Shapley's cluster-rich node, where gravity piles up, We can also talk about the biggest coherent underdensities, where matter is missing but geometry is strong and evolution is rapid. Both have scale, both affect motion, and both are part of the same web, carved from the same initial fluctuations. At this point, the narrative tension sharpens, because the web invites our pattern-seeking instincts and our desire to name what we see. Superclusters already stretch the meaning of an object, because their edges depend on method and on the data's completeness. Yet surveys keep revealing alignments and extended features that look even larger, sometimes spanning regions that feel uncomfortably vast. Some of these features appear to approach the scales where we expect statistical uniformity, and that is where the stakes rise. This is where the cosmological principle re-enters as a testable expectation, not a philosophical comfort we accept by tradition. Standard cosmology predicts that beyond a certain scale, structures should not remain coherent in a way that violates homogeneity in a statistical sense. The web should average out, even if it looks dramatic locally, because the initial fluctuations were small and nearly scale invariant. If we find structures that are too large and too coherent, we must ask whether they are real, or artifacts of selection, or simply rare extremes consistent with statistics. Selection effects are not a footnote at these scales, because our maps are built from incomplete samples and complicated pipelines. Surveys have magnitude limits, meaning faint galaxies drop out with distance, and the map thins unevenly in a way that can mimic structure. They have sky coverage gaps, including the zone of avoidance and practical observing constraints that leave holes. They have redshift uncertainties, and those uncertainties smear structure along the line of sight, especially when features are thin. Even the algorithms that find filaments and superclusters can shape the outcome, because they translate a point cloud into named features. If we choose a linking length that is too generous, separate features can be merged into one giant, creating a headline-sized structure from modest connections. If we smooth too aggressively, thin filaments can vanish and nodes can broaden, changing perceived coherence. If we smooth too little, noise can masquerade as structure, and the web becomes a hall of mirrors. The map is a measurement, but it is also an interpretation, and interpretation must be disciplined. Redshift space adds another complication, because it distorts shapes along the line of sight in ways that are easy to misread. Peculiar velocities can stretch clusters into fingers of God in redshift maps, long spikes caused by random orbital motions inside bound systems. Large-scale infall can compress structures in the Kaiser effect, flattening features toward overdensities and enhancing apparent contrast. Without careful correction, geometry can be mistaken for physics, and the largest claims can be the most fragile. Even distance indicators used for peculiar velocities carry systematics that are easy to underestimate, especially when combining heterogeneous datasets. Calibration errors can create spurious bulk flows or erase real ones, particularly if different methods have subtle offsets. Sparse sampling can bias reconstructions towards smoother fields, hiding sharp basins and ridges and making boundaries look more certain than they are. The most dramatic flow maps are powerful, yet they must be read as models constrained by data, not as direct photographs of gravity. Still, the broad picture holds across methods and decades, and that consistency is meaningful in a field where details can be contentious. Matter is arranged in a web, not as isolated islands, and the web's statistics match the growth expected from the CMB's initial conditions. Gravity and expansion together sculpt that web, and dark matter provides the dominant framework that collapses first and guides baryons. Superclusters are the named regions where the web's nodes and filaments become locally dominant, and where our definitions become part of the science. So what do Laniakea and Shapley reveal about the limits of structure, beyond their impressive spans? They show that the universe can organize matter across hundreds of millions of light years, with coherent motions that can be measured and modeled. They show that motion can define structure when density alone is ambiguous, especially near boundaries where the web thins. They show that largest can mean a basin, not a body, and that is a conceptual shift. They also show what bigness does not mean. And this is where caution becomes part of wonder rather than a break on it. A supercluster's span does not guarantee it is bound as one object, because expansion can win at the edges and prevent a shared fate. A named boundary does not imply a physical surface, like an atmosphere around a planet, because the boundary can be a ridge in a reconstructed field. A connected pattern in a survey does not automatically challenge cosmology, because rare patterns can occur and selection can exaggerate them. The meaning depends on statistics, dynamics, and definitions, and the definitions must be spoken aloud. This chapter sits at a hinge in the series, where certainty about objects gives way to arguments about patterns, and where maps become hypotheses. We have moved from bound objects like galaxies and clusters to structures that can be partly unbound and partly futureless as wholes. The scale is larger, but the certainty about edges is smaller, which is an unusual trade. The mystery deepens because the universe is giving us patterns instead of walls, and we must decide how to interpret them. We can summarize the key physical idea in one line, and then unpack its implications without losing the thread. Peculiar velocities are the fingerprints of mass distribution on top of cosmic expansion, revealing where gravity is winning locally. When we trace those fingerprints, we see basins like Laniakea and nodes like Shapley, and we see ridges that separate their influence. When we include voids, we see that absence also organizes the map because underdensity shapes flow as surely as overdensity. And that raises a thought that lingers as the visuals widen again and the web begins to look almost abstract. If boundaries are defined by motion, are they features of the universe, or features of our chosen frame and reconstruction method? If the same region can be partitioned by density, connectivity, or dynamics, which partition best captures physical reality and which best predicts the future? The web does not answer in words, but it answers in correlations, in flows, in the quiet alignment of many galaxies across dark space. Now the documentary prepares to push past even this scale, into the controversial giants. Some surveys report large quasar groups and immense walls that appear to span gigaparsec distances, and the claims are as provocative as the visuals. These reports raise immediate questions about statistics, selection, and what counts as a coherent structure when sampling is sparse. They also raise the deepest version of the central question, because the stakes become cosmological, and the cosmological principle is no longer background. If the largest patterns keep growing with better data, do we ever reach a final biggest, or do we only reach larger contexts? Or do we only reach larger contexts where our definitions shift again, and the same web looks new under a different metric? The next chapter follows that tension into the great walls and quasar alignments, where the debate becomes part of the story. We leave superclusters behind, and we enter the frontier where maps, methods, and the cosmic principle collide. We have followed the cosmic web from clusters into superclusters, where boundaries already became arguments and definitions carried weight. Now we push into deep time, where the traces are rarer and the claims are larger. Visually, the map changes character as we pull back, and the feeling of scale becomes almost physical. Nearby, galaxies crowd the frame like city lights on a night satellite image, but at great distance that glow thins into scattered pinpricks. The colour palette cools as the familiar richness drains away, and the audience senses that we are leaving the local neighbourhood. Even the grid lines feel less trustworthy, because the data density itself is now part of the story. The camera seems to climb, and the familiar textures of filaments and knots begin to dissolve into something more abstract. At these distances, ordinary galaxies fade below survey limits, and the map thins unevenly across the sky. What remains is not emptiness, but a measurement boundary, an edge drawn by sensitivity, exposure time, and the physics of faint light. To keep mapping, astronomers rely on beacons that can outshine whole galaxies, even when the rest of the scene goes dim. These objects are not gentle markers placed for our convenience. They are extreme engines that announce themselves across billions of years. Their light is not just bright, it is information-rich, carrying spectral lines that survive the long journey. Quasars are active galactic nuclei powered by accretion onto supermassive black holes, typically millions to billions of solar masses. In the simplest picture, gravity does not merely pull gas inward, it converts falling matter into heat and light with brutal efficiency. The deeper truth is that the energy comes from the gravitational potential well, which is steepest close to the event horizon. That efficiency is not a metaphor, because accretion can convert a significant fraction of mass into radiation. Nuclear fusion in stars is powerful, yet accretion onto a black hole can release more energy per kilogram. For a spinning black hole with a well-formed disk, the conversion can approach a few tenths of the infalling mass, an astonishing bargain, paid for by gravity. Gas spirals inward through an accretion disk. where friction and magnetic turbulence stir the plasma and raise temperatures to millions of degrees, the disk is not a solid object, but a rotating flow where angular momentum must be transported outward for matter to fall inward. That transport is the hidden machinery of accretion, and without it the gas would simply orbit forever. Magnetic fields thread the disk, and instabilities churn it like a stormy sea, turning ordered motion into heat. In modern models, magnetorotational instability acts like a cosmic gearbox, coupling neighbouring rings of gas and draining angular momentum. That hot disk radiates across the spectrum from ultraviolet through optical and into X-rays, with a luminosity that can rival 1 trillion suns. Around the disk, fast-moving gas clouds produce broad emission lines, and more distant clouds produce narrower ones. Those spectral fingerprints are not just decoration. They are the ruler marks that let us measure redshift and infer distance. Each line is an atomic transition, and each shift is a record of how much the universe has expanded since the light left. In practice, the spectrum is a layered story, with different regions contributing different features at different velocities. The broadline region can move at thousands of kilometers per second, while the narrower lines often come from calmer gas farther out. When we split the light with a spectrograph, we're effectively listening to several zones at once, each speaking in a different Doppler accent. Some quasars also launch jets, narrow beams of particles and magnetic fields moving near light speed. These jets are thought to be powered by magnetic fields anchored in the disk or the spinning black hole itself. When those jets point toward us, the quasar can appear even brighter, and the selection of what we detect becomes subtly distorted. Relativistic beaming makes the jet side aimed at us look amplified, while the opposite jet can nearly vanish. This is one reason quasar catalogues are not neutral portraits of the universe, because orientation quietly shapes what gets counted. In a deep survey, the sky can become biased toward the loudest directions, not the most typical objects. A quasar is not a typical galaxy, and it's not a stable long-term phase for most galaxies. It is a brief, violent episode, often triggered by gas inflow or mergers, that can flare and fade over tens of millions of years. During that episode, the nucleus can outshine the combined starlight of its host, turning a normal galaxy into a beacon. That timescale sounds long in human terms, yet it is a blink compared with the age of the universe. When we see a quasar at high redshift, we are watching a short-lived engine lit in a young cosmos. The light has crossed expanding space, stretched into redder wavelengths, and arrived as a delayed report from an earlier era. The youth matters because the early universe had more cold gas available and more frequent interactions between galaxies. Quasars become, in a sense, signposts of an era when growth was rapid and feedback was fierce. Their radiation and winds can heat gas and drive outflows, processes that may regulate star formation and reshape the host environment. That visibility makes quasars useful as markers of large-scale structure at high redshift, where ordinary galaxies become difficult to count. They act like distant lighthouses, revealing where matter and galaxies were concentrated long ago. Yet even as we use them as markers, we have to remember that they are not passive tracers. They are selective, episodic, and extreme. The visuals here want to be stark, almost minimalist, so the audience feels the scarcity. A dark sky map fills the screen, then bright quasar points ignite one by one, and suddenly a faint skeleton of structure seems to appear. The camera drifts across the map as if searching for coastline in fog, and the coastline only exists where the beacons happen to be lit. We can even let the points pulse gently, as if they are breathing across time, because each dot is a message from a different epoch. The emptiness between them is not truly empty, it is simply beyond the reach of our tracer. In that gap, galaxies still exist, dark matter still dominates, and gas still flows along filaments we cannot fully see. But quasars are biased tracers, because they appear only in certain galaxies and only during certain times. A quasar map is not a full census of matter, and it must be interpreted statistically. The map is closer to a weather report than a photograph, describing probabilities rather than drawing hard borders. Bias, in this context, has a technical meaning that is easy to misunderstand. Quasars prefer massive host environments, and massive environments already live in denser regions of the cosmic web. The result is that quasars overrepresent peaks in the underlying matter field, the way mountaintops dominate a skyline even when most land is lower. In the language of cosmology, Quasars occupy particular dark matter halos, and those halos cluster more strongly than the average matter field. The map therefore exaggerates contrast, making dense regions look even denser relative to the mean. This is not deceit. It is a predictable consequence of how rare objects populate the hierarchy of structure. There is also a duty cycle problem, because a galaxy can host a quasar and then go quiet. Two identical regions of matter can look different if one happens to contain more galaxies caught in the active phase. The duty cycle turns the cosmic web into a flickering display, where the underlying scaffold is steady but the lights are intermittent. This is not merely an observational nuisance because it changes the meaning of absence. A blank patch in a quasar map does not necessarily mean a void in matter. It can mean a quiet interval in the lives of black holes. The silence might be temporary, or it might reflect environments where fueling is less efficient, and the distinction is hard to see from far away. Large quasar groups, or LQGs, emerge from this statistical approach to mapping at extreme distances. They are associations of quasars that appear clustered beyond what randomness would suggest. The keyword is appear, because the grouping is a statement about a catalogue, not a direct measurement of a continuous wall. Historically, this kind of grouping became compelling as quasar catalogues grew from dozens to thousands, and then to tens of thousands. Each new survey did more than add points. It changed the kinds of patterns that could be tested. The transition from hand-plotted maps to automated catalogues also changed the sociology of discovery, because algorithms began to propose structures before human intuition did. The story of quasars themselves has a history of surprise, because they were first recognized as distant only when their spectra were understood. Early on, their star-like appearance misled observers, until redshift revealed their staggering distances and power. The realization that a point of light could be a galaxy-scale engine reshaped extragalactic astronomy, and it set the stage for using quasars as cosmic markers. An LQG is not necessarily a bound object, and it is not a solid wall of matter you could imagine flying through. It is a pattern found in a sparse set of points, interpreted as a large-scale overdensity. In the best case, it indicates that the underlying matter field had a broad enhancement there, even if the enhancement is not a single contiguous slab. To define an LQG, researchers use clustering algorithms that link nearby quasars into groups based on separation. A key choice is the linking length, the maximum separation allowed for membership. That separation is usually expressed in co-moving units, which keeps the comparison consistent across cosmic time, even when expansion changes physical distances. The method often resembles a friends of friends approach, where each quasar can recruit neighbours within a chosen distance. If those neighbours recruit their own neighbours, the group can grow in a chain-like way across the map. This chaining is powerful, but it is also dangerous, because a long structure can be built from a sequence of barely connected steps. The linking length is not a law of nature, and it is not measured with a telescope. It is a parameter chosen to balance two risks: fragmenting genuine structure or artificially stitching separate regions together. The choice can be motivated by expected clustering scales, but it remains a methodological decision, and that is why it attracts scrutiny. If the linking length is small, the map fragments into many small groups that look like islands. If the linking length is large, separate regions can merge into one giant structure that looks like a continent. The audience should feel this as a visual tension, because the same sky can tell different stories with a small turn of the dial. This is where definitions become physics adjacent, even when they are methodological. The chosen parameters can change the reported size, shape, and even existence of a group. When a structure is sparse, the definition is not a footnote, it is part of the measurement. The visuals can make this tangible, and the honesty of the demonstration matters. Lines appear between quasar points, then the narrator turns a dial, and the lines lengthen until separate clusters suddenly connect. We can pause on the moment of connection, one new bridge, and the map story changes instantly. That single visual beat captures why debates can hinge on what looks like a minor technical choice. The bridge might represent a real filamentary corridor, or it might be a statistical coincidence, and the algorithm cannot know the difference. The question becomes whether the bridge persists when the catalogue is perturbed, the parameters are varied, and the selection effects are modelled. The algorithm also depends on survey completeness and selection functions across the sky, which are rarely uniform. If the survey misses quasars in some regions, gaps can look like edges, and edges can look like walls. the footprint of the survey can become a ghost structure, faint but influential, overlaying the cosmology we are trying to infer. Even the act of observing introduces structure of its own, and that structure can masquerade as cosmology. A survey footprint has boundaries, variable depth, and regions masked by bright stars or poor imaging conditions. In the visuals, we can show those masks as translucent scars across the sky, places where the universe is present, but the data are absent. In some sky areas, the data are deeper, so fainter quasars enter the catalogue, thickening the tracer field. In other areas, the same population remains invisible, and the map quietly becomes patchwork. The patchwork is not a failure. It is a reminder that the sky is not observed all at once, and not observed equally. Redshift adds another layer of uncertainty, because distance is inferred from spectral shift rather than measured directly. Peculiar velocities are smaller at these scales, but redshift errors still blur three-dimensional positions. The blur is not usually dramatic for one object, yet it matters when the structure is defined by marginal links. A quasar's redshift is usually measured from emission lines, yet those lines can be shifted by outflows and complex gas dynamics. The result is that distance becomes a probability distribution, not a single perfect coordinate. In a narration beat, we can linger on that idea. Each point is really a small cloud of possible locations stretched along the line of sight. This matters because an apparent chain of quasars can be tightened or loosened by small shifts in inferred distance. A structure that looks thin in redshift space can thicken, or even fragment when uncertainties are treated properly. At the edge of a group, a few objects can drift in or out depending on how conservatively the errors are handled. Even when redshifts are accurate, the sample is not uniform with distance because of flux limits. As we look farther away, we see only the brightest quasars, and the tracer field thins. The thinning is a selection effect with teeth, because it changes the apparent clustering strength and the kinds of hosts we are sampling. The thinning is not just fewer points, but a change in what kinds of quasars we see. At high redshift, we preferentially detect the most luminous, often most massive systems, which increases bias and complicates comparisons across epochs. If the tracer population evolves, then the map evolves too, and we must separate cosmic growth from catalogue change. In that thin field, the boundary of any claimed structure becomes probabilistic rather than geometric. The structure is a region where the odds of clustering rise, not a surface you could cross. We can visualize this as a heat map that fades gradually, rather than a hard outline that snaps into place. With that caution in place, we can face the headline claims that define this chapter. They sound like the universe is building continents across gigaparsecs. The language is tempting because it translates statistical associations into geography, and geography feels concrete. One of the most discussed examples is the Huge Large Quasar group, often called the Huge-LQG. It was reported as an exceptionally extended association of quasars at high redshift. The excitement was immediate because the reported extent seemed to rival the scales where cosmology expects the universe to smooth out. The reported scale is on the order of billions of light-years, often described as several gigaparsecs in extent. By everyday intuition, that is larger than many expect any coherent structure to be. Even by professional intuition, it demands careful phrasing, because coherence at that scale cannot mean gravitational binding in the usual sense. To visualize a gigaparsec, the narration needs a slow breath and a patient comparison. The Milky Way is about 100,000 light-years across, and a gigaparsec is more than 30,000 Milky Ways laid end to end. We can add a second comparison that lands emotionally. Light would need billions of years to traverse the claimed span, even if space stopped expanding. We can layer the visuals, first showing our galaxy as a thin disk, then multiplying it into a long chain that stretches beyond the frame. Then we zoom out again, because even that chain is still small compared with the claimed span. The camera should hesitate for a beat, as if it is unsure whether the mind can hold the number. The claim matters because it seems to press against the cosmological principle, which underwrites modern cosmology. If structures remain coherent on multi-gigaparsec scales, homogeneity begins to look threatened. The tension is sharpened by the word wall, which implies a continuous barrier, even when the data are discrete points. Yet the Huge-LQG is also a lesson in how claims are constructed from sparse data and definitional choices. The group is identified by linking quasars that meet a chosen separation threshold. What the algorithm calls one object might be, in physical terms, Several overdense regions connected by chance alignments change the threshold, and the membership can change dramatically, especially near the edges where the density is lowest. A few bridging points can connect regions that would otherwise be separate. Those bridges are where the argument lives, because the bridge decides whether the headline reads largest group or several nearby groups. Those bridging points are visually seductive because they create the impression of continuity. On a sky map, a single dot can act like a keystone, and suddenly the algorithm declares a continuous structure where the eye already wanted one. The seduction is amplified by our habit of reading proximity as relationship, even when the third dimension is uncertain. The seduction is amplified by the way humans read maps because we treat lines as promises of reality. A line between 2 points feels like a filament, even when it is only a statistical link. In the visuals, we can make the lines slightly translucent, reminding the audience that they are hypotheses, not photographed bridges. The statistical significance is the next battleground, because large surveys contain many chances for patterns. If you search widely enough, unlikely alignments will eventually appear. This is the look elsewhere effect, and it is not a minor technicality in big data cosmology. When many groupings are tested, the most extreme one can look meaningful even if it is a statistical fluke. The catalogue is a landscape of opportunities for coincidence, and algorithms are tireless explorers. The deeper question becomes whether the most spectacular structure is also the most robust, or merely the most discoverable. There is a psychological component here that science tries to discipline, because our brains reward coherence. Humans are pattern detectors by evolution, and sparse cosmic maps invite the same instinct that finds shapes in clouds. The documentary can acknowledge this gently, because it is not a flaw in scientists. It is a feature of perception that statistics must correct. Significance thresholds must account for the number of trials, the algorithm's flexibility, and the survey's inhomogeneities. Without that accounting, a rare pattern can be overinterpreted. A result can be unlikely in isolation, yet entirely expected once you consider how many different ways the data were sliced. In practice, researchers compare the observed catalogue to mock catalogues that mimic the survey's selection and geometry. If similar large groups appear frequently in the mocks, the observed group becomes less extraordinary. The mocks are not an escape hatch. They are the proper baseline, because they include the same observational blind spots. Sample completeness matters in a more subtle way, because incompleteness can create artificial bridges and artificial gaps. If some regions are undersampled, the algorithm can misread the topology. The cosmic web can be turned into a connect-the-dots puzzle with missing dots, and the missing pieces can change the picture. Imagine a true overdensity with missing data in its center, perhaps due to masking or shallow imaging. The algorithm might split it into 2 groups, and then a different parameter choice might reconnect them through a thin corridor of points. The same physical region can therefore be described as 2 islands or 1 continent, depending on how the sampling holes align. There is also the issue of quasar bias and duty cycle, which complicates interpretation of any large quasar association. A true matter overdensity might host quasars intermittently, leaving a patchy and time-smeared signal. The wall, if it exists in matter, is not lit all at once, and our catalogue is a snapshot of scattered moments. Time smearing is easy to forget because the map looks static and complete. Each quasar we plot is seen at a different cosmic moment, and the structure is assembled from light that left at different times. Even within a narrow redshift slice, the light travel time across the slice can be tens or hundreds of millions of years. We are not seeing a frozen wall, but a stitched panorama of activity across a long interval. In the visuals, we can show this by sliding a thin time window through the structure, letting some points wink out while others appear. The audience feels that the wall is not a single moment, but a montage, so the Huge-LQG sits in a grey zone between discovery and artifact, where both possibilities remain live. It may trace a genuine large-scale enhancement, while its reported size depends on choices and chance. The honest stance is not indecision for its own sake, but recognition that the measurement lives near the limits of the tracer. This is not a dismissal, and it is not a confirmation, because the evidence is not a single decisive image. It is the frontier condition of cosmology, where the map is built from limited traces and strong assumptions. Frontier claims are often revised not because the science is weak, but because the data become less ambiguous. The deeper question is what we mean by a structure at these scales, which sounds philosophical, but is actually operational. Is it a connected set of points, a continuous overdensity field, or a dynamically meaningful entity? If the definition changes, the answer changes, and that is why the debate cannot be settled by rhetoric alone. At cluster scale, we could talk about binding, virialization, and edges like splashback that reflect real dynamics. At LQG scale, binding is not expected, and the edge is a statistical contour. The wall becomes a statement about correlation, not a statement about a single object holding itself together. That shift connects directly to the series' central question about bigness, because bigness can be defined in more than one way. The biggest claims often depend on the most interpretive definitions, and the definitions become part of the story. When we say largest, we must also say largest by which operational rule. Now the stakes rise again with an even more dramatic headline, one that pulls us away from quasars and toward explosions. The name itself signals a return to the language of walls. The Hercules, Corona Borealis Great Wall, is an enormous structure proposed from the sky distribution of gamma-ray bursts. It is often described as spanning several billion light-years. Unlike quasars, gamma-ray bursts are brief flashes, not persistent beacons you can revisit at leisure. They can be seen across extreme distances because they are among the most luminous explosions known, briefly outshining entire galaxies in high-energy light. A GRB begins as a spike of high-energy photons, sometimes lasting fractions of a second, sometimes minutes. Then comes the afterglow, fading X-ray, optical and radio light that can be chased by telescopes. In the visuals, we can show the burst as a sudden flare on a dark sky, followed by a shrinking halo that fades through wavelengths like cooling embers. The burst itself is detected by satellites that watch for sudden gamma-ray triggers, scanning wide swathes of sky. The afterglow is where the precision happens, because it can be localized and studied with spectra. Without that afterglow, the event is a flash without a reliable address, and a wall cannot be built from anonymous sparks. GRBs are linked to catastrophic events, including the collapse of massive stars and compact object mergers. Their afterglows allow redshift measurement, turning a transient into a distance probe. The physics differs by class, yet the observational challenge is shared, because the universe does not wait for our schedules. You must catch the event quickly, localize it precisely, and secure follow-up before the afterglow vanishes into noise. This urgency shapes the catalogue, because some bursts occur when telescopes cannot respond, or when weather and scheduling intervene. The wall, if inferred, is therefore built from what was catchable, not from what simply existed. In principle, GRBs can trace star formation and massive stellar deaths across cosmic history, because massive stars live fast and die young. In practice, they are sparse, and the sampling is uneven across the sky. A GRB map is more like a set of lightning strikes than a steady constellation, and lightning is never evenly distributed in time. A GRB catalogue is not a uniform survey of the universe, and it never pretended to be one. Detection depends on satellite coverage, trigger thresholds, follow-up success, and dust obscuration in host galaxies. Even the energy spectrum of the burst matters, because instruments have different sensitivities, and the same event might be detected by one mission and missed by another. Dust matters because it can hide optical afterglows, which makes redshift measurement harder. That means some bursts enter the catalogue as positions without distances, like pins without labels. The missing labels are not random, because dusty environments and faint afterglows correlate with host properties and viewing conditions. The catalogue therefore carries an imprint of astrophysics and instrumentation at the same time. That makes selection bias central to any large-scale claim based on GRBs, because the biases are not subtle. If some regions have better follow-up, they will appear artificially rich in measured redshifts, and richness can masquerade as structure. Sparse sampling also amplifies the human instinct to connect dots, because empty space looks like a meaningful gap. With few points, chance clusters can look like a coherent wall, especially when the search region is flexible. The documentary can hold this tension visually. Points are few, the distances are vast, and the mind wants to draw a boundary anyway. The proposed Hercules, Corona Borealis feature is inferred as an overdensity in GRB positions at similar redshifts. The reported span becomes enormous when translated into co-moving distance. Co-moving distance is a standard cosmological coordinate that factors out the expansion of space, so that early and late epochs can be compared consistently. It is useful, but it can sound like a physical ruler laid across a present-day object. But locomoving size is not the same as a physical object with a current boundary you could outline on a map. It is a coordinate measure, powerful for theory, easy to misread in headlines. We can show this visually by letting the universe expand in an animation while the comoving grid stays fixed. The wall's comoving span remains constant, even as physical distances change with cosmic time. The audience hears the subtle point. The coordinate is stable, but the intuitive picture of a rigid wall can be misleading. The statistical debate echoes the LQG debate, but with even fewer traces and more complicated selection. With small numbers, the uncertainty on clustering measures becomes large, and significance is fragile. Here, a single new burst with a measured redshift can shift the apparent strength of a feature. That sensitivity is not a flaw in arithmetic, it is the consequence of working near the limits of data. The look elsewhere effect returns in a sharper form, because many partitions of the data can be tried. Different redshift slices, sky cuts, and clustering metrics can produce different walls, and the most dramatic one is not automatically the most reliable. Selection effects can also imprint apparent anisotropies, because satellites do not observe the sky uniformly over time. Even small exposure differences can matter when the dataset is sparse. The visuals can underline this with honesty and restraint rather than spectacle, because the argument is about method, not about drama. We see the GRB sky plotted, then an exposure map overlays it, revealing that empty regions may simply be regions less watched. We can then fade in a randomized catalogue that respects the same exposure pattern, showing how apparent clusters can arise. The comparison makes the argument without turning it into a verdict. So the Hercules, Corona Borealis Great Wall, becomes a case study in the limits of mapping at extreme distance. It may hint at real large-scale structure, while remaining vulnerable to sampling artifacts. The most responsible posture is to treat it as a hypothesis under stress testing, not as a finalized continent on the cosmic globe. These controversies do not happen in a vacuum, because cosmology carries an expectation about large scales that is both empirical and philosophical. That expectation is the cosmological principle, a working rule that the universe is homogeneous and isotropic on sufficiently large scales. It is not a claim that the universe is bland, but a claim that the statistics settle down when the volume is large enough. Homogeneous does not mean smooth everywhere, and isotropic does not mean featureless in every direction. It means that when we average over large enough volumes, no direction or location is special. The principle has a history, and it did not emerge from one measurement or one era. It grew from the broad success of cosmological models, from the uniformity of the cosmic microwave background, and from the way large surveys begin to look statistically similar when smoothed. The cosmic microwave background is especially persuasive because it is a snapshot of the early universe with tiny temperature variations. Those variations are real structure seeds, yet their small amplitude supports the idea that the universe is close to uniform on the largest scales. Cosmology also speaks of a scale of homogeneity, often cited around 100 to 300 megaparsecs in co-moving terms. Beyond that, fluctuation should diminish in relative amplitude, even though rare features can exist. Claims of multi-gigaparsec walls create tension because they seem larger than that scale, and they force us to ask what exactly is being measured. The tension is not immediate falsification, but it demands careful statistical framing and careful language. A key point is that homogeneity is statistical, not absolute, and that distinction matters. A homogeneous universe can still contain large filaments and voids, as long as they are consistent with expected fluctuations. Another key point is that our observations are not direct samples of matter, which is mostly dark. They are samples of traces, and traces have biases that can mimic or exaggerate structure. This is where the documentary's earlier lessons about edges return with new force. At the larger scales, the edge is not a boundary in space, but a boundary in inference. We can frame the problem in accessible statistical terms without losing rigor, because the idea is familiar. In small datasets, patterns appear easily, and the most striking pattern is not always the most meaningful. As distance increases, the number of traces per volume drops, and the map becomes noisier in 3 dimensions. The uncertainty grows, and the temptation to overconnect grows with it. Even if a clustering signal is real, its shape may not be a single coherent wall that wraps the sky. It could be multiple filaments and nodes aligned in projection, or linked by algorithmic choices. Projection is a quiet villain in large-scale claims because 3-dimensional structure is inferred from redshift. Small redshift uncertainties can smear thin features into thicker ones, especially when the tracer density is low. Survey geometry is another quiet villain, because holes and depth variations can create apparent boundaries. A wall can be partly the edge of where we looked well, and partly the echo of where we did not. The documentary can let that land as an observation about humility. Our maps contain both universe and instrument, intertwined. So we should treat these Great Wall claims as hypotheses about the cosmic web's extremes, rather than final cartography. They are prompts to improve surveys, refine statistics, and test robustness across methods. At the same time, the mystery is not manufactured, because the cosmic web truly is immense and physically motivated. Simulations and galaxy surveys agree on a universe threaded by filaments and punctuated by voids. Those simulations begin with tiny fluctuations in the early universe, then let gravity amplify them over billions of years. The result is a network where matter streams along filaments into nodes, and emptier regions expand into vast voids. In the visuals, we can crossfade between a simulation's dark matter skeleton and the observed tracer points that only hint at it. The audience sees the gap between what is there and what we can currently draw. The skeleton looks continuous, while the data look like scattered sparks, and the mind must do the interpolation. Some filaments and walls are unquestionably real on hundreds of megaparsecs, and they are not controversial. They are the natural outcome of gravitational growth from tiny early fluctuations. The open question is how far that coherence can extend before it becomes a statistical mirage, created by sparse sampling and flexible definitions. The answer depends on better tracer catalogues, better selection modelling, and better null tests. Null tests are essential because they ask what patterns appear in randomised or simulated catalogues built to match the survey's biases. If the same algorithm finds similar walls in mock data, the claim weakens, and the weakening is informative rather than embarrassing. Robustness tests are essential because they vary linking lengths, redshift cuts, and completeness corrections in controlled ways. A real structure should persist across reasonable choices, not only one. If it vanishes when a single parameter shifts slightly, then its grandeur may be more about method than about matter. There is also a deeper observational humility embedded in these methods, even when the debate sounds sharp. We are mapping the deep universe through a keyhole, and the keyhole changes with instrument and method. When the keyhole changes, the map changes, and that is not scandalous. It is the normal process of frontier measurement. The question is whether the claimed wall survives when the window widens. The central question returns in its sharpest form, and it is both scientific and human. How big can the largest structures become, and what do their sizes reveal about our limits of knowing? The answer for now is double-edged and therefore honest. The universe contains genuine vast patterns, while our maps can also manufacture vast patterns from sparse points. So the Great Walls remain both invitation and warning, and the tone should stay suspended between awe and caution. They invite us to imagine structure on scales that strain language, and they warn us that inference can outrun evidence. As the visuals linger on a sparse sky map, a thought becomes hard to avoid. When we draw lines between distant beacons, are we revealing the universe's architecture, or revealing our own need for coherence? We end this chapter with a deliberate uncertainty that is still grounded in physics and in method. The cosmic web is real, but its farthest outlines are still being negotiated by data. And that sets up the next pivot in the series, from the largest debated structures to the largest compact objects. After walls measured in billions of light years, we turn to horizons measured in light hours. Next, we leave statistical edges behind and approach a physical edge that general relativity defines exactly. We move toward black holes, where size is the radius of a boundary that light cannot cross. After walls measured in billions of light years, we turn to horizons measured in light hours. We descend from the cosmic web into a different kind of enormity, where darkness has a precise boundary, and scale becomes strangely intimate. The camera that once drifted past filaments and voids now tightens its focus, as if the universe invites us closer to a single, severe detail. We trade panoramic structure for one exact curve in space-time, an edge drawn not with matter, but with causality. A black hole is not defined by what it contains, but by what it hides from every outside observer. Its size is the event horizon, the surface where escape speed equals light speed, and the universe's fastest messenger finally loses. That definition sounds simple, yet it carries a profound implication that is easy to miss on first hearing. The horizon is not a place you can touch, because it is not made of atoms. It is a boundary in the geometry of space-time itself. In Einstein's general relativity, gravity is not a force pulling through space like an invisible rope. Gravity is the bending of space-time, and the horizon is where that bending becomes so steep that every future-directed path points inward. In the language of physics, the horizon is a causal boundary, separating events that can influence infinity from events that cannot. It is less like a cliff in space, and more like a change in the rules of time, because inside, later always means deeper. Imagine a map where every road slopes downhill toward a single basin, and the slope grows steeper the closer you get. Outside the horizon, you can still choose routes that lead outward. At the horizon, the last outward route disappears. If we could overlay light cones on that map, they would tilt like windblown trees in a storm. Far away they stand upright, offering many future possibilities. Near the horizon they lean inward, until the only remaining futures fall toward the centre. In the simplest non-spinning case, the horizon radius is the Schwarzschild radius, named for Carl Schwarzschild's 1916 solution to Einstein's equations. It scales linearly with mass, because the curvature produced by mass-energy adds in direct proportion when you pile on more mass. The formula is compact and famous, r equals 2 times g times m divided by c squared. It is a rare moment where cosmic drama reduces to 3 constants and a single variable, and the constants are the same everywhere. For intuition, the rule is blunt and memorable, and it holds across an absurd range of scales. Each solar mass adds about 3 kilometers to the Schwarzschild radius, so doubling mass doubles the horizon, and tripling mass triples it again. That number is not a coincidence or a convenient rounding for documentaries and textbooks. It comes from the speed of light being enormous, so it takes a great deal of mass to make the escape speed reach c. Escape speed is a Newtonian idea, but it points toward the relativistic truth in a way our intuition can grasp. When the required escape speed reaches light speed, the geometry has already become extreme. So extreme that even light cannot find a path outward. This is the first twist in our scale story, and it is a twist that feels almost unfair. A black hole can gain mass without gaining bulk in the ordinary sense, yet its boundary still grows predictably, as if the universe provides a built-in ruler. A planet grows by adding layers of rock and metal, and its surface is a physical crust you could stand on. A black hole grows by adding mass energy, and its surface is a mathematical threshold that nothing locally feels as solid. The event horizon is not a material shell, and it is not a hard surface waiting to be struck. It is a geometric threshold in space-time, where light cones tip so far inward that out stops being a direction. That phrase, light cones, can sound abstract, so translate it into plain language and a simple visual. It means that even if you fire a rocket at full thrust, every possible future you can reach still leads deeper inside. Outside the horizon, gravity can be extreme without being fatal at once, depending on mass and distance. Inside the horizon, the concept of outward direction fails, and light itself cannot return to report what it finds. This is why the horizon is sometimes called a point of no return, although it is really a surface. It is the last place from which a signal can still, in principle, reach the rest of the universe. If size is the horizon, then largest object becomes a question of mass and nothing else. Black holes turn mass into a ruler, and general relativity supplies the conversion with an elegance that feels almost unsettling. Yet even here, a caution hides in the clarity, because nature rarely gives us perfect textbook cases. The horizon radius is a clean measure for an idealized black hole, while real black holes spin, accrete, and live inside turbulent magnetized plasma. Spin matters because it changes the metric, reshaping the horizon and altering what radius even means in different directions. In practice, we often quote an effective size, but the true geometry is richer, more like a distorted sphere than a simple circle. We meet the first class in the hierarchy, stellar mass black holes, born from the collapse of massive stars. They form with typically a few to tens of solar masses after nuclear fuel is exhausted and pressure support fails. In the final moments of a massive star's life, fusion can no longer provide outward pressure against gravity's inward demand. The core collapses in a fraction of a second, and the outer layers may rebound in a supernova or fall back in defeat. If the remaining core mass is high enough, Not even neutron degeneracy pressure can hold it up for long. The collapse continues, and an event horizon forms, quietly, invisibly, before any light can announce it. The physics is brutal and precise, because collapse is a runaway once key supports vanish. Temperature rises, densities soar, and space-time itself becomes the arena, until the boundary appears and the outside universe loses causal access. Their horizons are small on human scales, tens of kilometers across, comparable to a city commute. They can hide inside a city, yet their gravity can shred a star, because tidal forces rise steeply as you approach. The useful image is a star drifting too close, stretching into a luminous ribbon as different parts fall at different rates. The process has a name, spaghettification, and it is a reminder that gravity's gradient, not just its strength, governs destruction. On screen, we can watch that ribbon brighten, twist, and snap into a swirling stream that wraps the whole. Hot gas glows blue-white in X-rays, and the final plunge happens in darkness because the last photons are trapped. Stellar mass black holes were once theoretical curiosities, discussed in the shadow of neutron stars and supernovae. History moved fast, and by the late 20th century, X-ray binaries revealed compact objects feeding on companions with masses that ruled out neutron stars. Those systems told their story through motion and light, a two-part signature that was hard to fake. Gas heated in a disk radiated X-rays, while orbital dynamics constrained the unseen mass, and the numbers pointed to horizons rather than surfaces. Then came gravitational waves, a new sense entirely, predicted by Einstein and finally captured a century later. LIGO and Virgo heard the chirps of merging stellar mass black holes, converting tiny ripples in space-time into direct evidence that these objects are common. The waveform is not just a detection, it is a measurement, because its pitch and sweep encode masses and spins. In those rising tones we hear the last orbits, the plunge, and the ring down, space-time vibrating like a struck bell. Next come intermediate mass candidates, the missing middle that would connect stellar remnants to galactic giants. They may range from hundreds to hundreds of thousands of solar masses, but the census remains incomplete, and the evidence often arrives indirectly. This gap matters because nature rarely leaves clean holes in a distribution without a reason. If intermediate mass black holes are rare, it tells us something about how black holes form and how environments feed them. Some candidates appear in dense star clusters and dwarf galaxies, where gravity packs stars into close quarters. Their existence matters because they could be seeds for the supermassive giants, bridging the leap from stellar remnants to galactic monsters. In a crowded cluster, repeated mergers and runaway collisions can build a heavier object over time. In a small galaxy, a central black hole might grow quietly, then later be delivered to a larger galaxy through mergers. We can visualize that delivery as a slow dance of galaxies, their stars barely colliding but their dark halos interpenetrating. As the galaxies merge, dynamical friction drags the black holes inward, until two dark centers become one. Then come the supermassive black holes, millions to billions of solar masses, and they change the tone of the story. They are not rare curiosities, because most large galaxies host one at the center, like a dark anchor hidden in the brightest core. This is a crucial bridge back to earlier chapters, where boundaries were statistical and edges were negotiable. Galaxies and clusters had fuzzy limits, but their centers often contain a boundary defined exactly, a curve in space-time that does not care about our conventions. The Milky Way's own central black hole, Sagittarius A, makes that point personal and almost intimate. We cannot see its horizon directly with our eyes, yet we can watch stars orbit an unseen mass with clockwork precision. Those stars trace tight ellipses over years and decades, and the best-known, S2, swings around the center at thousands of kilometers per second. At closest approach, it dives through a region smaller than our solar system, and still the mass remains dark. But we cannot fly there with a tape measure, and we cannot weigh it with a scale. We weigh supermassive black holes across cosmic distances by watching how nearby matter moves, because motion is gravity's handwriting. The cleanest method is dynamics in nearby galaxies, where resolution is high enough to isolate the center. Stars and gas orbit under gravity, and their speeds reveal the enclosed mass, just as planetary orbits reveal the sun's mass. If we resolve individual stellar motions, we can model the gravitational potential with detailed orbit families. The challenge is separating the black hole's pull from the surrounding star's mass, which can mimic a central concentration if we are careless. Astronomers build models that include stellar density profiles, orbital anisotropies, and the telescope's blurring, because every instrument smears reality. A small uncertainty in the central light profile can translate into a large uncertainty in the inferred dark mass. For gas disks, we measure rotation curves and line widths, and we worry about turbulence and pressure support. Cold Messier disks can be especially powerful, because their geometry is simple and their velocities are precise, traced by microwave emission from water molecules. Those masers act like bright beads embedded in a rotating ring, each one a tiny lighthouse in a distant nucleus. With very long baseline interferometry, we map their positions and velocities, turning a faraway quasar host into a measurable, three-dimensional dynamical system. Farther out, we use ionized gas and stellar absorption lines, but the clean simplicity begins to fray. We fit orbit libraries and anisotropies, and the uncertainties rise with distance and complexity, because real galaxies are not perfectly symmetric. Dust lanes obscure parts of the nucleus, bars stir non-circular motions, and turbulence broadens lines beyond pure rotation. Each complication is manageable, yet together they remind us that precision is earned, not assumed. In active galaxies, the nucleus outshines the host, and dynamics becomes harder because the glare washes out the stars. So we use time instead of sharp images, and time becomes a ruler, measured in days, weeks, or months of delayed light. Reverberation mapping tracks echoes in the broadline region, a region too small to resolve directly at most distances. Variations in the accretion disk's light are followed by delayed responses in emission lines, as if the gas clouds are answering a call. The delay gives a light travel size for the broadline region, and it is a wonderfully direct idea. Combine that size with the line widths, and we infer a virial mass for the black hole, assuming the gas is gravitationally bound. The logic is simple in outline. Faster line widths imply stronger gravity, while longer delays imply larger radii. Together they constrain the mass, much like measuring both the speed and distance of an orbiting body. This method is powerful because it works when we cannot resolve the center, and it reaches deep into cosmic history. It is also model dependent, because geometry, inclination, and cloud physics are uncertain, and a flattened disk seen edge-on can mimic high velocities. Astronomers fold those unknowns into a calibration factor, tuned using nearby galaxies where dynamics provides an anchor. That calibration is an achievement, yet it also means that systematic error can travel across cosmic time. We also model the accretion disk's spectrum, especially in luminous quasars where the disk dominates the output. The disk temperature profile depends on mass and accretion rate, though degeneracies remain, because dust, inclination, and winds reshape the emitted light. A thin disk radiates like many black bodies stacked together, hotter inside and cooler outside, and the sum becomes a broad continuum. The peak shifts with mass, so a heavier black hole tends to have a cooler disk for the same relative accretion rate. At the largest distances, we often rely on scaling relations, because detailed modelling becomes impractical. Black hole mass correlates with bulge velocity dispersion and bulge mass, linking the nucleus to the galaxy, as if growth and structure negotiated a long-term contract. These relations are empirical and useful, but they scatter, and the scatter is astrophysics speaking through noise. At high redshift, they may evolve, and selection effects can bias which systems we detect, because the brightest quasars are not a fair sample of all black holes, so every mass estimate carries error bars that matter for our biggest claims, especially for record holders. The farther back we look, the more we infer and the less we directly measure, until a single assumption can tilt a headline number. Now we pivot from weighing black holes to understanding why we see them at all, because the hole itself is dark. A black hole itself is invisible, but its feeding can light up the universe, turning hidden gravity into visible fire. Accretion is the engine that turns gravity into radiation, and it is one of nature's most efficient power plants. Gas spirals inward, heats through turbulence and magnetic stresses, and shines before crossing the horizon, because friction and magnetic reconnection convert orbital energy into heat. In a sense, the light is the cost of losing altitude in a gravitational well paid in photons. Matter falls inward, and the energy it releases can be a significant fraction of its rest mass, far more efficient than nuclear fusion in stars. As the gas compresses and shears, it forms an accretion disk, and the disk becomes a laboratory for plasma physics. The disk is not smooth like a vinyl record. It is a churning, magnetized fluid where instabilities transport angular momentum outward. Angular momentum is the real gatekeeper, and it explains why black holes can be surrounded by bright structures instead of simply swallowing everything. Matter cannot simply drop straight in, because it carries rotational motion, so it must shed that rotation through torques, turbulence, and magnetic fields before it can cross the horizon. The magnetorotational instability, driven by differential rotation in a weak magnetic field, is one of the key mechanisms. It turns ordered rotation into turbulence, and turbulence into transport, allowing gas to drift inward, while energy is dissipated into heat. That light can exceed the combined starlight of the host galaxy, and it can do so for millions of years. In a quasar phase, a small region can dominate an entire cosmic neighborhood's energy budget, outshining billions of suns from a volume smaller than our solar system. Visually, a quasar is a point of brilliance with faint ghostly structure around it, and the contrast is almost violent. The host galaxy becomes a dim halo, while the nucleus burns like a lighthouse whose beam is made of ultraviolet and X-rays. There is a limit, and it is another boundary like an edge, though it is not geometric. The Eddington limit is where radiation pressure outward balances gravity inward for ionized gas, set by the tug-of-war between photons and electrons. Photons carry momentum, and when they scatter off electrons, they push, and that push adds up. In a fully ionized plasma, electrons are coupled to protons, so that push can lift the whole gas, even though gravity pulls mostly on the massive protons. If luminosity rises too high, radiation pushes in falling matter away and throttles growth, like a furnace blowing back its own fuel. The limit depends on mass, so larger black holes can sustain larger luminosities, which is why the brightest quasars imply enormous central masses. This sets a timescale for growth under steady Eddington-limited accretion, and the timescale is not arbitrary. To reach billions of solar masses early, black holes must grow efficiently and quickly, doubling again and again on a cosmic clock that is still ticking. That is a major cosmological puzzle, and it is not just a detail for specialists. Quasars appear when the universe was less than 1 billion years old, yet their masses imply rapid assembly, as if the cosmos built skyscrapers before it finished laying streets. Possible solutions compete, and none is fully settled, which keeps the story open and alive. Seeds could start larger from direct collapse, accretion could be super Eddington, or mergers could accelerate growth, especially in the dense early universe where encounters were frequent. Direct collapse imagines a massive gas cloud avoiding fragmentation into stars, collapsing nearly monolithically into a heavy seed. Super Eddington accretion imagines geometry and radiation, trapping allowing inflow to continue, despite intense luminosity. Mergers add mass in discrete jumps, but they also raise another question that is easy to overlook. When black holes merge, gravitational waves carry away energy, and the remnant can recoil. So how often does a growing black hole get kicked from its own fuel supply? Feedback complicates every path, because the engine fights its own hunger as it shines. The same radiation, winds, and jets that announce accretion can also heat and expel gas, starving the engine. So growth is not just about supply, but also about self-regulation. This is where black holes connect back to the structure story, and the connection is not metaphorical. They are not just passengers in galaxies, because their energy can reshape galactic evolution, altering star formation, gas inflows, and even the temperature of surrounding halos. Jets can drill through interstellar and intra-cluster gas, remaining narrow over astonishing distances. Winds can sweep out star-forming material, and radiation can change the cooling balance of entire halos, turning a galaxy's central region into a battleground between collapse and escape. In images, jets appear as narrow beams ending in radio lobes, like cosmic exclamation points written across intergalactic space. They inflate cavities in hot gas, leaving bubbles that show up as dark voids in X-ray maps. Those cavities are not empty, even when they look like holes punched in the glow of a cluster. They are filled with relativistic particles and magnetic fields, and the work required to inflate them is enormous. That work is one of the clearest signatures that a black hole can heat gas far beyond its own horizon. Energy deposited in the right place can prevent cooling, and that prevention can change the fate of an entire galaxy or cluster core, In clusters, this becomes a thermostat problem we met with the Phoenix cluster, and the metaphor is surprisingly accurate. Cooling gas wants to condense, but AGN feedback often reheats it and prevents runaway, keeping the cluster core in a delicate, time-dependent balance. Hot intracluster gas radiates X-rays, and without heating it should cool, sink, and form stars at a prodigious rate. Yet many cluster cores do not form stars nearly as fast as simple cooling predicts. Phoenix showed the thermostat can fail or lag, and that failure is scientifically valuable because it reveals the mechanism. It hints at timing, geometry, and coupling, and it reminds us that black holes can regulate the largest bound systems, not by size, but by power delivered to the right place. So black holes are small in radius, yet large in consequence, and that contrast is the chapter's heartbeat. Their size is a boundary, but their influence can extend across galaxies and into cluster cores, shaping environments that are measured in thousands of light years. Now we approach the extreme case that makes the numbers feel unreal, and we do it by following the light. We meet TON 618, a quasar powered by one of the most massive known black holes, a name that sounds technical yet points to something almost mythic. TON 618 sits at great distance, seen as it was when the universe was much younger and more crowded with gas. Its light has travelled for billions of years, stretching as the cosmos expands, arriving at Earth as a message from an earlier epoch. On screen, we can let that travel become a visual, a beam thinning and reddening across expanding space. The quasar's point-like glare hangs against a field of faint galaxies, and the background looks calmer than the physics that created it. TON 618 is often cited at tens of billions of solar masses, and the phrase itself strains comprehension. The exact value depends on methods and assumptions, but the scale is consistently enormous, and even conservative estimates place it among the heaviest known. Those masses are typically inferred from broad emission lines and luminosity, using calibrated relationships that tie line width to orbital speed and brightness to the size of the emitting region. It is a chain of inference, strong but not unbreakable. The broad lines come from fast-moving gas close to the centre, where velocities reach thousands of kilometers per second. The width is Doppler broadening, a spectral fingerprint of motion, and the motion is gravity made visible. Apply the horizon rule and the boundary swells in a way that feels almost like a trick of units. 3 kilometers per solar mass becomes hundreds of billions of kilometers for a tens of billions solar mass black hole, a number so large it begs for translation. In astronomical units, the event horizon radius is on the order of hundreds of AU, and that is a startlingly familiar scale. That is comparable to the outer solar system, where sunlight is weak and the planets move with slow, cold patience. For intuition, Neptune orbits at about 30 AU, and Pluto averages near 40 AU, far beyond the warmth of Earth. A horizon of hundreds of AU would reach far beyond those familiar distances, swallowing the Kuiper Belt's inner realm in a single invisible circle. Picture the Sun at the centre of a clean diagram, with planetary orbits drawn as thin rings and labels floating in the dark. Now replace the Sun with a black hole, and draw the event horizon as a thick band that sweeps past Neptune's path. Then let the diagram dissolve into a more physical scene, a dim, icy frontier of comets and dwarf worlds. The horizon is not a glowing rim, so we mark it with a faint translucent ring, an artist's boundary for a boundary that would not shine. This comparison is the chapter's central shock, because it collides with our everyday sense of small. A single object's no-return boundary can be larger than the planetary region where our instincts place space, and it forces a recalibration of what compact can mean. Yet the second shock is the correction that keeps us honest, and it is essential for perspective. Even a solar system-sized horizon is tiny compared with a galaxy's size, and it is almost negligible compared with the vastness of the dark matter halo. The Milky Way spans about 100,000 light-years in stars, and its dark halo extends much farther into the surrounding darkness. A horizon measured in AU is microscopic by that standard, like a grain of sand measured against a continent. So big splits into two meanings, and the split is the core lesson of this chapter. Black holes can be big in mass and gravity, while remaining small in spatial extent relative to galaxies, which is why they can sit at galactic centers without filling them. Their significance is density and curvature, not volume, and curvature changes what distance even means near the center. They concentrate mass into a region where space-time geometry dominates every other physical intuition, and where the familiar separation between space and time begins to blur. Even the word surface is misleading, because nothing solid is there and nothing waits like a wall. The horizon is a coordinate-invariant boundary, defined by the causal structure of space-time, meaning its existence does not depend on how you choose to describe motion. That clarity is rare in this documentary's scale ladder, and it is worth pausing on for a beat. Clusters had R200 and splashback, superclusters had watersheds, and great walls had statistical edges, all useful but all dependent on definitions and thresholds. Here, general relativity gives a boundary with a clean equation, and the equation does not negotiate. The darkest giants have an edge we can define, even when we cannot see it directly, and that definability feels like a rare foothold in the dark. But definition does not mean simplicity, because the real universe adds rotation, fields, and chaos. Spin changes the horizon and introduces an ergosphere, and real black holes live in messy environments of plasma and fields, where magnetic lines twist, reconnect, and launch outflows. A spinning black hole drags space-time around with it, an effect called frame dragging, and the effect is not subtle near the horizon. In the ergosphere, nothing can remain at rest relative to distant stars, and energy extraction becomes possible in principle. That possibility is not just science fiction, because it connects to how jets may be powered in real systems. Magnetic fields anchored in the disk can tap rotational energy, and the result can be a collimated outflow that carries power far beyond the nucleus. Still, the linear scaling remains the key, and it is the ruler we carry into the extreme. More mass means a larger horizon, and the conversion is one of the universe's starkest relationships, linking an invisible boundary to a number we can estimate from light. We can now ask how TON 618 fits into cosmic history, and the question has weight beyond a single object. A black hole that massive implies long-term fueling, early seeding, and a host environment that supplied gas, again and again, without shutting the engine down too soon. Its quasar light is a sign of accretion, not of the horizon itself, and that distinction matters for interpretation. We infer mass from emission lines and luminosity, and we carry the uncertainties forward because the horizon is not what shines. At high redshift, those uncertainties widen, and the widening is part of the story rather than a footnote. Broadline region geometry, orientation, and calibration can shift the mass, yet the conclusion remains extreme, because even a substantial downward revision leaves a black hole of staggering scale. There is also a subtle observational bias that shadows every record holder, and it shapes our sense of the cosmos. The brightest objects are easiest to find, so the most massive black holes may be overrepresented in our catalogues, while quieter giants remain hidden in dimmer galaxies. TON 618 is not the biggest thing in the universe by size, and it does not compete with walls or horizons of cosmology. It is a demonstration that compact objects can reach masses that rival small galaxies' stellar content, compressing what could have been billions of suns into a single gravitational identity. This loops back to the central question about what size reveals and what it hides, and the loop tightens our theme. A horizon tells us about mass, but not about the full reach of influence, because influence is written in jets, winds, and the motion of surrounding matter. A galaxy's edge is fuzzy, but its stars fill space and broadcast their presence in light. A black hole's edge is sharp, but its gravity and feedback can sculpt structures far beyond its radius, reaching into regions where stars form and gas cools. So the documentary's hook returns with a darker twist, and it changes how we interpret scale itself. If we could zoom out forever, bigness would not only be distance, but also depth of gravity, the steepness of the cosmic well carved into space-time. Consider the strange inversion at the heart of black holes, a fact that sounds wrong until you do the math. The most massive can have weaker tidal forces at the horizon than smaller ones, because the gradient can be gentler when the horizon is larger. For a stellar mass black hole, the horizon is so close to the center that the difference in gravity across a body can be lethal. For a supermassive giant, the horizon is far enough out that you could cross it before tides become catastrophic, at least in principle. That observation raises an unsettling question about experience versus definition, and it lingers like an echo. If crossing a horizon might not feel dramatic locally, what does it mean that the boundary is still absolute for the rest of the universe? From outside, the horizon is an edge in causality, and the story ends there, no matter what the infalling traveller experiences. From inside, the future narrows, and the geometry dictates the outcome, and the gap between those viewpoints is part of black holes' enduring mystery. And now the chapter's tension pivots toward the final question, because our ladder of boundaries is not finished. If even black holes have a definable boundary, what is the biggest boundary of all? The one that might encompass every galaxy, every quasar and every wall. Is there an edge to the universe itself? Or only horizons set by time and expansion and the finite speed of light? Does beyond mean a place, or a limit to what can ever be observed, no matter how advanced our instruments become? We leave the darkest giants and move toward the largest limit we can see. Next, we confront the observable universe, cosmic horizons, and the geometry of expansion, where the boundary is not a surface in space but a limit in space-time. The scale ladder ends where observation ends, and mystery begins again, with a boundary that is real but not a wall. The question is not only what lies outside, but whether outside is even a meaningful word. We leave the darkest giants and move toward the largest limit we can see. The central question returns, because the biggest things depend on definitions and horizons. On screen, the scale bar keeps stretching, kilometers to light years to gigaparsecs, until numbers start to feel like weather. The universe has an edge that is not a wall, because light and time set it. The particle horizon marks the farthest matter we can observe today, given 13.8 billion years. It's a boundary drawn by causality, traced by the oldest photons we can still intercept. That distance is not 13.8 billion light-years, because space expanded during the journey. In Comoving terms, the observable radius is about 46.5 billion light-years, and the diameter is about 93. The same photon can travel for billions of years, while the intervening metric quietly grows beneath it. Expansion needs plain language, because it sounds like a speed limit violation. Galaxies are not racing through space faster than light, because space itself stretches between us. A helpful visual is a grid that swells smoothly, carrying dots apart without any dot breaking local physics. As the metric expands, distant galaxies recede, and their light is redshifted. The wavelength is stretched with the space it crosses, an imprint we read as a shift toward infrared. Beyond a certain distance, recession can exceed c without breaking relativity, because no local object outruns light. This is why the cosmic horizon is a space-time boundary, not a physical rim. It is also why distance has multiple meanings, including light travel, proper distance, and co-moving distance. Each one answers a different question, and the universe punishes us for mixing them casually. Historically, these ideas did not arrive all at once. In the 1920s, Hubble's redshifts turned nebulae into galaxies and expansion into evidence. Later, the cosmic microwave background, faint, uniform, and ancient, made the horizon feel almost tactile, like a glow at the limit of time. A second horizon matters even more for the far future. In an accelerating universe, the event horizon is the limit of what we can ever influence, or ever receive new signals from. It is the boundary of possible conversation, even if we had perfect engines and infinite patience. Dark energy drives that acceleration, and it changes the fate of structure. Over immense timescales, galaxy groups become isolated islands, while more distant galaxies slip beyond the event horizon. The night sky would slowly simplify. Fewer external galaxies, less new information, and a growing silence between gravitational oases. The sky does not end, but our causal reach does. The observable universe can still grow in comoving volume, while the set of reachable targets shrinks. That contrast feels paradoxical, yet it follows directly from how expansion reshapes the future light cone. So what is the largest object, now that the horizon frames every claim? The largest gravitationally bound structures are galaxy clusters and their dark halos, defined by conventions like R200 and by edges like splashback. These definitions are not arbitrary labels because they connect to density thresholds and to the orbits of infalling matter. Clusters are big because they are bound, and because most of their mass is dark. Their outskirts are gradients, yet their dynamics give a physical meaning to size that walls often lack. In X-ray and lensing maps, you can almost see the invisible, hot gas glowing, and background galaxies subtly sheared by gravity. The largest luminous single objects are giant galaxies and brightest cluster galaxies. Their reported diameters depend on surface brightness limits, intra-cluster light subtraction, and where we decide the galaxy fades. A galaxy can have a bright core and a ghostly envelope, and the envelope may blend into the cluster's shared starlight. The largest compact objects are supermassive black holes, where size is an event horizon. A horizon is sharply defined by relativity, yet the mass estimates still carry model dependence at high redshift. We infer them through stellar motions, gas dynamics, and accretion signatures, methods that agree broadly, while still leaving room for systematic uncertainty. The largest claimed patterns are walls and quasar groups stitched from sparse traces. Their sizes can reach gigaparsecs, but their reality depends on statistics, selection effects, and how we link points. When the map is thin, the eye wants to connect the dots, so the analysis must ask whether the pattern survives random chance. This is the reframing that closes the loop from Chapter 1. At cosmic scales, object can mean a bound entity, a luminous body, a compact horizon, or a debated overdensity pattern. The word sounds simple, yet it hides a choice about physics, measurement, and what counts as a coherent thing. The cosmological principle survives by being statistical, not absolute. The web can be dramatic on hundreds of megaparsecs, while still averaging toward homogeneity on larger scales. In wide-field surveys, filaments and voids look like a nervous system. Then, with more distance, the texture softens into near uniformity. Now the oldest question returns, asked in a new key. Where does it end, and what does beyond even mean when the horizon is defined by light and expansion? The camera can drift outward until galaxies become pixels, then noise, then a smooth background that refuses to become a boundary. We do not know whether the universe is finite or infinite in extent. Measurements of curvature suggest near-flat geometry, yet near-flat can still be finite, and inflation predicts regions far beyond our horizon. A sphere can look flat when you stand on it, and a cosmos can look Euclidean when your view is limited. Beyond the particle horizon is not necessarily nothing, and not necessarily an edge. It is simply unobserved, and perhaps forever unobservable, depending on the future expansion history. The thought is unsettling and elegant. Reality may extend, while our evidence remains permanently local. This is the final connection to the human edge of space. The Kármán line was a threshold of atmosphere and engineering, and the cosmic horizon is a threshold of causality and time. One boundary is crossed by rockets and heat shields, while the other is crossed only by patience, inference, and mathematics. Both boundaries are real, yet neither guarantees the end of reality. They tell us where our definitions work, where our instruments reach, and where physics limits what can be tested. Even so, the boundaries are productive. Each one forces better questions, sharper models, and more careful language. So the answer to how big the largest objects can be is conditional. The biggest bound things are clusters, the biggest compact things are black holes, and the biggest patterns are arguments. Each category reveals a different limit: gravity's cohesion, relativity's horizons, or statistics' caution. The quiet conclusion is that every new map expands the known and sharpens the unknown. There may be no final biggest, only larger contexts, and a horizon that keeps moving with us. And as we look outward, we're also looking backward, into the history of light, and into the rules that decide what can ever be seen. We started with an edge that was never really an edge, the Kármán line, and learned that big begins as a human contract. From there, the scale ladder forced new languages, AU, light years, parsecs, and new cautions, because distance, brightness limits, and lensing can quietly rewrite what we think we see. Galaxies taught us that size is not a clean outline but a fading gradient, where dark halos stretch far beyond starlight and definitions depend on depth. Clusters then became the first truly heavyweight contenders, their borders drawn by conventions like R200 and R500, or by a more physical splashback radius that marks where infalling matter turns around. Superclusters and walls push the question into stranger territory, where largest becomes a flow field, an algorithm, or a statistical pattern in the cosmic web. And when we turn toward black holes, the biggest boundary shrank to a horizon only light hours across. Absolute in causality, almost unremarkable to cross locally, yet final for everyone watching from outside. Even the Phoenix cluster reminded us that extremes are not just large, they are instructive, exposing where our feedback stories bend or break. TON 618 and other early quasars did the same, hinting that the universe can build giants faster than our simplest growth rules allow. or that our measurements still carry hidden biases. Finally, the observable universe reframed every earlier largest claim, because the widest boundary we can draw is not a wall in space. It is a horizon in space-time, set by the universe's age, the finite speed of light, and an expansion that can hide regions forever, even if they continue to exist. Taken together, the chapters point to one consistent lesson. The cosmos offers edges we can define, but rarely edges that are truly physical. The more carefully we measure, the more we discover that object, structure, distance, and size are categories with assumptions, useful, testable, and sometimes negotiable. So the largest things are not only the ones with the greatest diameter or mass, but the ones that force us to say what we mean. A galaxy ends where our surface brightness threshold gives up. A cluster ends where we choose a dynamical boundary, and a wall exists only if statistics survive every mock universe we can build. When we ask whether the universe violates homogeneity, we're also asking how we sample it and how we decide what counts as real. Some patterns may be genuine architecture, others may be the shadow of sparse traces, survey footprints, and linking lengths that chain chance alignments into apparent continents. And yet the mystery is not a failure. It is the point of the exercise. Scale is both measurable and elusive because our best rulers are made of light, and light arrives with history attached. What we can say with confidence is that bound structures have a natural ceiling set by gravity competing with cosmic expansion, while unbound patterns can sprawl as far as initial conditions allow. The universe does not promise a single champion. It offers a hierarchy of big, each level revealing a different kind of limit. In that sense, the journey from Earth's sky to the CMB is not a tour of bigger and bigger objects. It is a tour of different meanings of boundary. Some are engineering thresholds, some are dynamical edges, some are causal horizons, and some are simply where our data thins into uncertainty. And still, every step outward has made one thing clearer. The largest structures are not just out there, they're also in our methods. The universe expands our maps, but it also expands the questions those maps are allowed to answer. In the end, biggest is not a single trophy we can place on a shelf. It is a moving target that depends on what we can define, what we can test, and what we can ever observe. That is the thread tying everything together, from the gradual fade of atmosphere to the gradual fade of certainty at the edge of the observable cosmos. We do not reach a final border, we reach a point where the next border is made of inference. And that is why the largest objects in the universe are never just objects. They are arguments between nature and our definitions. Each time we zoom out, we don't just find a larger thing, we find a larger context that changes what the previous thing meant. If there is a limit, it may not be a maximum size, but a maximum clarity, set by horizons, by selection effects, and by the stubborn fact that we only see along our past light cone. So the story closes where it began, with the feeling that distance can become almost meaningless, not because measurement fails, but because meaning keeps shifting with scale. And that shift is the real revelation. The universe is not only vast, it is layered, and every layer demands a new definition of what counts as real. So where does bigger finally stop? At the edge of space, inside a black hole, or in structures so vast they shouldn't exist? The answer is that it doesn't stop at a single place. It changes form, from practical edges to gravitational edges to statistical edges, until the final boundary becomes a horizon of what can be known. The edge of space is a convention, a black hole's edge is a causal verdict, and the edge of the cosmos is the limit of shared history. What bigger reveals is not a final object, but the universe's habit of turning size into a question about definitions, dynamics, and time. Maybe the most honest, largest object is the one we can never fully draw, the universe beyond our horizon, not smaller than our imagination, just unreachable by our light. In that silence at the edge of observation, scale becomes a kind of humility, measured in numbers and felt as mystery. Because the farther we zoom out, the less we find a last thing, and the more we find that reality is made of boundaries that are real and boundaries that are chosen. The cosmos doesn't end with a biggest, it ends with a deeper question. What does it mean to know where anything ends? If you want to keep following that question, look up how your favourite largest claim is defined and ask what would falsify it, because the next discovery will begin with that discipline.